Okay, so today is my one cup of coffee day where I get really messed up and code a lot for like 16 hours, like two 8-hour sessions. So let's see if we can pull this off, or if we didn't get enough sleep and the coffee is just gonna make us jittery and paranoid, but not productive. We'll see. I feel like I got enough sleep, but I don't know. I woke up with a headache, so let's give this a shot. Now, I see it doesn't say I'm recording yet. Hold on. I should be recording. My OBS software says I'm recording. There we go. Okay, I just want to make sure everything looks good. Okay, so, with that said, we left the code in a broken state on Saturday, which is something you shouldn't do, but we were a little bit delirious, so we decided, between the two bad choices that we were stuck making, the best choice was to throw an error where we were kind of left off, and that way we could get back there and do whatever we needed to do. Okay, so here we put this little error here. If U value is fractional, we need to round up that value and pull the rectangle in to be 511 instead of 512. Basically, if rectangle started out odd, there is no way to correct it back to exactly 512. So, yeah, so this floating point value that we're using as a check value actually could be useful for solving some problems here. So this check value actually is kind of invalid, because if it doesn't match, actually we want to do something useful with that. Here's what we're gonna do. And I know that, you know, I've been reading more of well, not reading, well, yeah, kind of reading Mike Acton from Insomnia Games. I've been looking at some of the stuff he posts online, and he would hate me for adding unnecessary branches to code. But, you know, we gotta get things working first. So let's get things working first, and, you know, things might get a little bit ugly. So, so this thing right here, this commentary, can actually go up here. And I noticed that right now, we're indented, like, super far, right? So, I don't want to have to deal with this. So we're just going to say, we're just going to say, you know, pull more if U is fractional. And is it a pull, or is it also a push here? If the width is greater than 512, yeah, so we're actually pulling it in, yeah. Pull more if U is fraction. Let's say fraction like that, okay? And then over in our comment file, we'll just paste that in there, right? Because it's this long commentary where we're really not gonna wanna read this long commentary anytime soon. So we'll just kind of throw it here to, you know, be there forever in this little archive of random comments. And if somebody is ever really curious about the whole sentence, right, then somebody can find it, right? And we can do at vid iid, and it is 0065, and the time is 4 minutes 27 seconds. And it's actually 0 hours, so I guess we should probably put 0h like that. And the date, if we want to do the date, if we want to be really meticulous, and I don't know if this is a good idea to be this meticulous, like maybe it's just a waste of time. Okay. We were originally crashing here, but what we really want to do is, if the values aren't equal, we want to just increment the U value. So, U equals U plus 1. Right? Because we have this fractional thing, and this is basically a seal, right? It's a seal of F, right? That's what's actually happening here, is a seal of F, but we don't need any fancy seal function, right? We already know, we already have the U value, right? So effectively we're doing a seal, but you know, let's not make the code harder than it already is, right? So this is for the width, and we need the same kind of logic for the height as well. So if we look at the height, we have this U value and this C value, and we want to make sure that, you know, if they don't match, we want to add to the U value as well. So we can take the same exact logic, and we can kind of like put it down there as well. And I think, did we do the formulas for this, or are we missing some stuff, or did we do the math? It looks like we did the math. So let's say this is also U, and that looks pretty good to me. Now, I do want to kind of like diff these somehow visually really quick. So the first way to do that, I'd like to do it kind of hackishly if I can. Like take a screenshot of both of these and see like if they match exactly except for the X's and Y's, which is kind of a hacky thing. It only really worked in MS Paint. Do I have like a Paint 95? Paint 95. I used to have Paint 95, or Paint XP. God damn it, Paint XP. I used to have Paint XP, or Paint 95, and those were great. Like, sometimes tools are great until people add more and more features to them, right? And, it's like you can only add so many features to a hammer before the hammer is complete, you know? And then everything is just a stupid idea. So what we're gonna do is, this code is way too long. I gotta say, it's like to actually get my bearings here, because it kind of like goes off the screen like this. It's not, I do not like this. I do not like this. We're gonna try to simplify this. We're gonna take this commentary, and this is our little math proof, right, for fixed number 001. What is this? So this is for, this is the pulling back math. So we're gonna say, we'll call this, zoom correction pull in math. So we'll call it zoom correction pull in math, because we just want to declutter this, because the clutter is actually really getting to me here. And this is, we solved everything algebraically on the x-axis for how to kind of pull that. If the zoom rectangle is larger than 512 by 512, then we want to pull in the bounds on the x and y, and we do it component by component. So we do the width, the x's first, and then do the height. And we only solved it for the x, because for solving it for the y, it's the exact same calculations, right? But let's take this little notation here, zoom correction pull in math, and let's just throw it over here. Because it's just cluttering things up. You know, all we really did is we solved the problem algebraically, because it was easier. Like, I usually like to solve things very visually and geometrically, but sometimes it's easier to wrap your head around things with, like, simple algebra. So, we solved it algebraically. If the zoom rectangle is too large, over 512 wide, by 512. This is how we pull it back in and off. Okay, so we could also use modulus for our calculations. Like, we're doing this weird floating point stuff, which is really stupid, but we just want to get it working first. When we're pulling in and we're trying to, like, zoom in and out, the rectangle always grows by 2 pixels, because we at least pull in each edge by 1 pixel. We don't do anything fractional, right? All the math is discrete. And because of that, when we're pulling this 512 by 512, if we want to make that smaller, the next step that it's going to be at is actually 510 by 510, right? Because we got to pull in both edges. And so, when we have an odd-sized rectangle, we can't snap it to exactly 512 by 512. The best we can do is 511 by 511. So we're going to have to account for that. Now, in the future, we might want to make a constraint that says, well, the rectangle can only be, you know, evenly sized, right? And that would actually make a lot of math probably easier for us and make our lives easier. So we might want to think of some type of constraint like that. But for now, we're going to kind of just do the math, pretending that constraint doesn't exist, and we'll add on constraints later. Now, sometimes when the math is really difficult to comprehend, or the algorithm is really difficult to comprehend, you might want to add more constraints ahead of time, so that you don't have to think about all the complex. You can make a simpler algorithm, right? The more constraints you put, the less edge cases you have to think about, right? But in this case, we're not gonna add extra constraints and then simplify our algorithm. We're gonna do it without those constraints. Okay, so now that we've kind of like taken this and put this in here, let's say, can we make a smaller tag for this? Like, how about overgrow pull fix, right? And the reason why I want something a little bit shorter is just because it's already a little bit too cluttered, right? So let's say overgrow pull fix, and then we can put overgrow pull fix here, right? And the idea is that these tags, since they match, it's the same exact math, right? So then over here, we can kind of like make another label, right? And these are synonymous labels. And, okay. And then for this, we might want to say, you know, ditto for y-axis. Okay. And also, we might want to make a time at vid IID 0065. And the time is 0 hours, 13 minutes, and 18 seconds. Okay. And we can take the same kind of tag right here, and we can put it here as well, right? So, since we're going to make this commentary right here, we're going to need to explain it again, right? We can't just throw in like a little commentary tag and then not explain it again, because if somebody goes to this part of the video, we need them to instantly see what's there in the documentation, right? In our video documentation. So, right here. So, if our viewport gets too large, right, greater than 512 on the x-axis, then we're going to use overgrow pull fix. That's what this code here is. And we're just going to try to shrink the rectangle by the correct amount. So the formula, we solved this formula algebraically. So the math here is we take the x-bound, and we take the upper x-bound and the lower x-bound. And the upper x-bound needs to be pulled back, and the lower x-bound needs to be pulled forward, right? And that's going to make the rectangle collapse in on itself. So we take the modified bounds, and when we subtract them and add 1, the total width should come out to 512, right? So we do the math, and we just, let's say, like, solve it algebraically, right? So the first thing is we can get rid of this 1 and just make it 511, right? Because we know that's to account for the off by 1 error. Let's align this a little bit better. Once we've done that, we can take off the brackets by distributing the -1. So this negative sign can actually be thought of as a -1, and I had to ask my girlfriend for help on this, so she is the one who helped me with this, right? So you just take this and you distribute it into here, right? So it's a -1 times this, right? And when I think of it as a -1, then I'm like, oh yeah, of course you can distribute that, right? So -1 times this means that it's still negative, and then -1 times this u flips the u, right? And so now we have two negative u's. And the next thing is, we know that the those x boundaries are knowns, right? So we want to isolate the unknowns. So we're going to bring the 511 over to this side, right, by minusing it from both sides. And then we're going to take the u's, and we're going to put the u's on this side, right, by adding them, right, because they're negative here. So we'll add 2 u's over here and put the 2 u's over here, right? And now that we have these 2 u's, we might want to, well, divide it out, right? So before, we might want to duplicate this one more time, because we have this u plus u, and we might want to just make a note that that is u times 2, right? And I wrote it u times 2 because then it's easier to see the divide by 2, right? If we did 2 times u like this, it makes the logic a little bit harder to follow. I know it doesn't really matter too much, but I like to be able to follow things like that. So u plus u, and that's 2u, right? And then we're going to divide out, we're going to make this 1u, right, because we're solving for u. So we'll divide by 2 here, right, to get just u. And that also means that this formula up here, we also have to divide by 2, right? So let's line that all up. And then let's just color everything to make sure that everything is accounted for, right? So we have everything like that. Yeah, that looks good to me. Okay, so let's check the formulas and make sure that we actually did those correctly. So we have the boundaries. This is u. This is the final formula, right? So the upper bound, lower bound, 511. We got upper bound, lower bound, 511 divided by 2. That's our u value, right? Then the check value is the same exact thing, except we're using floating point. And then if they don't match, then that means we need to pull more if it's a fraction. So we're just going to do u equals u plus 1 to pull a little bit more. Because we can't pull by a fractional amount, right? So if we can't pull by a fractional amount, we need to overshoot. I guess technically maybe we call it undershooting, because we're trying to bring in the rectangle a little bit more than it needs to be, because the rectangle cannot sit on fractional bounds. Okay, so once we figure out that u value, right, we just adjust the lower bound and the upper bound accordingly, right? We bring in the lower bound, and we could think of it as this. We could think of it as, you know, x0 is kind of like going this way, or the 0 is going this way, and the upper bound, the 1, is going this way, right? So when we're kind of visualizing it, like, why are we adding to one and subtracting to the other one? Because the 0 is the lower bound, and the 1 is the upper bound, right? So we're kind of doing this kind of a thing, right? So now that we kind of have that all sorted out, we might want to consolidate this logic a little bit and make sure that it is identical on the y, right? So to make sure that it's identical on the y, what we could do is we could look for everything where it's like the 1s. We could color the 1s and the 0s. So let's say that the 1s are going to be orange and the 0s are going to be cyan, right? And we're not going to look at if it's x or y, because we just want to make sure that we have the same kind of colors when we go down into that y block. So if we go down into this y block, it's kind of hard because we scroll down and we don't see the other code anymore, right? And that's why I'm kind of annoyed that we're scrolling so much here. But let's take this thing right here, put it right here, right? And I don't know how it was adjusted. Okay, so we had a little padding right there. So let's take, let's actually take this height formula and let's throw it into our notes file really quick. All right, we got this notes file, and let's just temporarily paste it over here so that we can kind of cross-check it, right? Just make sure that it kind of matches how we think it needs to be, right? So this formula here and this formula right here, right? We're assuming that these are kind of like synonymous. These are synonymous formulas here, right? So if we look at this, let's just cross everything out one at a time. So right here we got upper minus lower minus 511 divided by 2. And what's this? We got upper minus lower minus 511 by 2. Okay, cool. And then this next formula right here is upper lower minus 511 divided by 2, but it's just floating point. So we got upper minus lower minus 511 by 2. Okay, so that is also good. Okay, what about the assert? We got the assert and FU equals FC. Is that correct? That is not correct because, right, because it's one's floating point, one's not. Oh, well, actually, no. If we do floating point and it's off by 1, that's going to truncate it, right? If we do a cast of a floating point, oh, we're not casting to integer, so that would actually be wrong. But I do like that assert. I do like the idea of asserting that the difference is only like half of a pixel, right? And so if we do an assert, but we do a cast to integer, this assert would actually be kind of useful. Now this assert, let's actually do this kind of assert right above here. So on the X, let's just throw it in, right? The more asserts, the better in terms of, you know, the mistake. So let's assert and cast this to integer and cast this to integer. Now that is kind of wasteful because one of them is already integer, but I just want to eliminate stupid mistakes that I could possibly make. So, you know, this is going to make sure that it's 1 delta. Or del 1. Delta 1. Let's just call it at delta 1. And then over here in our notes, we can make, well, what do we mean by at delta 1, right? And so let's just put it over here, right? And say that at delta 1, for this piece of code, in tau type.f means the delta of 2 values is exactly 1, right? And that's not always the case, right? We want to make sure that the delta is either 0 or the delta is 1, right? So that's not exactly what we're going for, and we need to check that assert statement one more time. So let's just add a vid IID, or a vid IID, and 0065, and the time is 0 hours, 23 minutes, and 6 seconds. Okay. So if we look at this delta here again, we have some type of assert, and... oh, no, because remember, it's just going to take that fractional value and it's going to floor it. So this is actually correct. And now that we know that's actually correct, we need to take this assert that we've kind of changed here. We need to put that right below here, right? This assert here, we're making sure that they are equal by casting them both to float. That's not gonna work out for us, is it? So we're gonna post that down there, and we're just going to give this another shot, right? So let's move this in, and right, I know we kind of lined this up as well. So float, if we cast a float, if they're not equal to each other, we're just going to pull more if it's a fraction. Okay, that's fine. And we just want to make sure that the indentation is, like, exactly the same. Now, I do think having a little... this little space here after this if is kind of helpful. And why are we... our error messages are kind of different here, aren't they? So this U here that we're using... oh, what's up with this? This is a... so right here is just a little check. Check to see if it's equal to exactly 512 or 512 minus 1, right? Because there's two possibilities for that. And making sure that the rectangle's in the proper order as well. So, you know, to keep this a little bit simpler, what we could do is we could say, you know, we could actually put these asserts, like, after these ifs, so that they're always getting ran rather than just running them in the branch, which might be kind of weird, because it's like we never corrected them, so why are we checking them? But then we get a little bit of extra error checking anyways, and then we can consolidate the actual logic in one place and then the error correction in another place. So I'm actually going to do that. So after we've actually corrected those values, why not just put the corrections, you know, over here, right? The little asserts. So we can take this assert, and then this assert here is not as robust as the X assert, so we need to look at them and be like, well, what is missing from one and what's missing from the other? So we see this is just to make sure that the rectangle is not inverted, right? The Y should be less than or the lower bound should be less than or equal to the upper bound, right? And then we're going to make sure that this equals 512 here, but that's not true anymore, right? It needs to be equal to 512 or 512 minus 1, right? Because of the fact that the rectangle may be an odd rectangle or an even rectangle. Now, if we really want to get this like proper, what we could do is we could say that what we really want to say is that well, we've already it's too late to do that check here. So, you know, let's just let's not worry about that, you know, this check is for if it's even and this check is if it's for odd. Let's not worry about that. Even though that is the case, so maybe we want to be a little bit more robust, because right now we're doing this weird floating point thing over here, and really we just need to check to see if it's an odd rectangle or even rectangle. And we could do that. We could, you know what, we could do that. So, why don't we do, how about wid odd equals 0, and then actually wid odd equals 1 until proven otherwise, and wid, and then height odd equals, so we're, and this is a little bit cluttery. I don't know if I like this or not. Let's just do it. So, int 32, and that kind of is ugly as well. But, let's just go with it. Let's just go with it, see what we got here. So in here, when we're looking at this, actually we don't need to do until proven otherwise. We can just do this. Wid modulus 2, right? And if it is even, we're going to get a 0, and if it's odd, we're going to get a 1, right? And then we can do this as well. So, right? Width and height. Now that we have this, like, modulus stuff here, we can actually, like, kind of double-check stuff here, right? So we can say that, right here, we're pulling more. We're expecting to pull more if we got, like, an odd rectangle, right? So we're going to assert that the, that wid odd is greater than or equal to 1, right? That we're assuming that this is an odd rectangle, right? So we're actually making the code a little bit, we're making the code less efficient right now, but we're just trying to be very paranoid and catch problems, right? We're adding like more redundancies so that we can catch problems in our logic, right? So we can optimize later. Right now, we just need to make sure that everything works, right? Because we got this cluster of code. It's kind of confusing. We just want to make sure that we can make sense of it, right? For this, I mean, we already have it indented like this, so why don't we just say, you know, assert valid size correction. Okay. So we could assert a valid size correction. And the other thing we can do is we can say that right? Because we're redoing the width and height. Why don't we just reuse those variables for the width and the height here? Why don't we just say that, you know, now why do we have, why do I have these two oh, because I see why I have these two calculations. We're recalculating this stuff twice just for readability. But, let's just say that width equals, and take this width, and then the height equals, and then we'll take this calculation here, right? Okay. So now that we have these calculations, we can say, yeah, assert that, yeah, that's fine. And instead of this, we want to be like, you know, if, now, why are we doing, so does this have to be exactly 512? Are we inside of a case right here? Are we inside of a case? So if the rectangle is too big, and we have the if width here, okay, and the if height. So now we're kind of like, we're outside of those branches, so we can't actually say that now, can we? We can't. If we put the error correction here, then we can't do that. So we'd have to re-wrap it in another case here. Yeah, that adds a lot of branching, doesn't it? I'm making this way too complicated. So let's just add more variables. Let's just throw more variables in. It's getting kind of ugly, but let's just do, you know, U08 width fix equals 0, and U08 height fix equals 0, right? So the width fix and the height fix, right? And so if the width is too large, then, you know, width fix equals 1. And if the height is too large, then we need to say that the height fix equals 1, right? So we're gonna fix those values, right? So, we can do a little marker here. We can do @vid IID 0065. And, the time is, so we're kind of running out of room. So I think what we could do is, why not try like 0, 0, 0, 33, and then 3310, like that, right? And then IID, and then like that, and then time is like that. That's kind of shorthand. I don't know if that's the best way to do this, but it's better than nothing, right? So, but if people are looking for vid IID, they're never going to find this, so I don't know if that's a good idea. But we only have room for this, so let's just throw it in like that. So the width fix and the height fix, just flagging to see if we needed to change those, right? So we have this guard here to see if it's over 512 and the stuff we're going to do, and we have the guard here to see if it's over 512. And if it is, we flag as having a height fix and a width fix, right? Let's actually move this. I don't know. I kind of like it like maybe this, right? And then width fix is kind of right there. And I can also kind of pull that in here like that. Okay, and let's just make sure these match. So now that we're kind of addressing this, why don't we do you know, the same kind of deal over here and just make it match, right? So we're looking at this still, and we can now say that 34 minutes, 31 seconds. So 34 minutes and 31 seconds. Okay. And we're just making sure that these blocks match, and that if the width needs correcting, we flag the width fix, and if the height needs correcting, we flag the height fix, right? And we need to make sure the indentation is kind of similar. That looks good there. So now we're recalculating width and height here, right, after we've done the fixes. And because we've recalculated it, we can, these asserts here are actually fine. We can put these asserts here, we can clump these asserts together like that. And for the width and whatnot, these actually need to be guarded to say, you know, if we did a width fix, then we're expecting these things. We're not just expecting these things, we're like expecting that if a width fix is greater than or equal to 1, we are expecting that, if, the width equals, if 512 equals the width, and, that would mean that it's an even rectangle, right? So if it's an even rectangle, right, we have this width odd, so the width odd would actually be equal to 0, right? So, and 0 equals width odd. If these are the cases, then we want to, you know, assert that the width, or 512 equals the width, right? Or, oh, we're not even asserting that. We're just saying, you know, do nothing. Good, do nothing. Or actually, we don't need a whole bunch of branches. We can do like this. So if it's if the width was odd, if the width was even, right, and then we're expecting 512 to be the width, and if it was the other case, if it was odd, then we're expecting 511, right? So we're gonna take this check, or like, oh, if it's either this or this, and we're giving this wiggle room for 512 or 511, we can actually encode that. We can be a little bit more strict, right? Now, we don't want to say 511 here, though. We actually want to say, like, 512 minus 1. And that's because, eventually, if we want to replace this with, like, some type of constant value, it's going to be easier if we use, you know, some type of value like that. So, now everything is getting kind of cluttered, right? And we're just running out of room in general. So, we do see that we have this width fix here, and basically we want, you know, if the width fix is greater, if it was actually fixed, right? Okay, so if it's this and one of these, right? One of these has to be true. So we can say this, and then either this or that, right? So we're going to get rid of this right here, like this, to try to give us some more room here, right? And let's actually kind of like do 512 and like plus 0, right? Just to make it more obvious that there's some kind of symmetry there. And then we'll take this. It's either one of these or one of those, right? So, oh god, this looks ugly. Okay, so if we actually fix the width, okay, and then, and if we fix the width, that's not quite right. Because what if we didn't fix the width? If we didn't fix the width, we don't care, do we? God, this sucks. Okay, so let's change that back. So if we fix the width, let's just keep it as simple as possible. So let's change this to, yeah, let's keep it more dead simple. And just say that, you know, and remove some of the indentation. So if the width is fixed, if this, we're okay, else, and then if This we're also okay, right? So we're just going to add extra branching, which might be inefficient, but let's not worry about efficiency. Let's just worry about getting it working. Else. And then here is an error, right? So bad shrink. X-axis. Okay. So, and we have these two guards here, so else if, we're kind of making this kind of ugly, right? Because we have these two guards right here, and we're kind of like reducing some of the indentation, but this is a guard saying, you know, if we didn't fix the width, right, then we're not going to worry about this, right? So, you know, we'll say, okay, even rectangle shrunk, and this is okay, and it's an odd rectangle that was shrunk. Odd rectangle shrunk. Okay, so that's pretty good. We have all this trash over here where we're trying to do these comparisons and whatnot. Let's just delete that trash. And the y-axis is the same deal, right? The y-axis, same exact stuff, it's just for the y. So assert valid size correction is what we're in, so that's good. So if the height fix is greater than or equal to 1, meaning we fix the height, then we want to do all the same stuff, but anywhere where we see width, we just want to replace that with height, right? A pretty simple deal, just find and replaces. And then bad shrink, and this is going to be a y-axis now, right? Bad shrink. Now, we might want to do like bad shrink 2020, and then do y-axis like that. That way we can see, if we want to, we can see these both are the same, and then we can see that these two are different, right? That might be a little bit helpful with our error messages. And that's all we need for kind of like calculating that the rectangle was properly shrunk. Now, I am kind of worried because we kind of like threw a whole bunch of stuff in here. You know, so we're hoping that everything is... Oh, crap. Hey, thank you. So, one of these days, I'm going to start coding before you. Yeah, one of these days I'll start coding before you, because, yeah, you keep on being so nice to me, and, I'm always coding after you. Hold on, so actually I'm gonna message you, because I don't know when that happened, so I'm just gonna message you, really quick here. Okay. So there's a little bit of lag. Let's just show kind of like what I'm, little tech demo really quick. And then we'll get back to this for a second, because I want to like show people kind of like what I'm working towards when, I see new people kind of pop in. So hold on. So AA1 GIFs. I'm going to open up this folder of stuff that I'm working on, and we're just going to show you stuff really quick. We're not going to get too much into it, because I know a lot of people have already seen this stuff. So we're just going to go through it really quick, and then we're going to get back to writing the code. So let's see, GIFs in Windows Slideshow, yeah? Okay, so basic idea is I made this game a long time ago, and It's done in Flash. It looks like it's done in Unity. I coded the lighting system, the physics, the explosion system. It's basically like Bomberman, except all of the bombs are proximity mines, and there's four-way explosions, vertical explosions, horizontal explosions, and then there's instant kill mines. So most of these bombs you can actually touch without them hurting you, except for the skulls. So once you touch a bomb, right, it lights up for a little bit, and then there's a little delay, it starts to blink, and then it explodes, and then chain reactions ensue. And unlike Bomberman, right, you can step right past the bombs and nothing happens. They don't block your way. So it's kind of like there's a proximity mine that's on the wall, right? Some things are a little fun, right? We're making like little obstacles you have to dodge. Different materials have different properties. I did AI so that AI tries to push you into the instant kill bombs there. Some materials are destructible and they leave nothing behind. Some materials are destructible and will leave a scaffolding you can climb behind. And then some materials are indestructible and don't even let flames pass through them. These vents here, the blue tiles you're seeing, they actually let flames go through them. And that way you can kind of create this indestructible tile that will let flames from chain reactions kind of pass through the material. Anyway, so this is kind of this thing I'm working towards with this engine, but it's going to be a fancier rendering engine. But anyways, let's get back to what we're doing. We have a rectangle, and the rectangle is used for our camera. So when we want to zoom in, we want to look at less tiles. So we go from a rectangle of, say, this size, and we pull in the edges, and we call that a zoom pull, and that effectively zooms in, right? So we're saying that the parameters for zoom pull, this last parameter needs to be a positive value, and it pulls the rectangle in, makes it smaller, and that effectively zooms in what we're looking at. Now, if we want to zoom out, right, it's exactly the opposite, right? So if our rectangle is this size and we want to zoom out, then we add a negative, and we grow the rectangle by pushing these sides out, right? Because this is called pull, but now we're pushing, right? To do the opposite of a pull, we do a push, and to do that, we invert the sign here, right? And a larger rectangle means that we can view more data within that rectangle, and therefore, if we're viewing more things in the viewport, then obviously they all have to be smaller, right? If there's only a single tile in this rectangle, then obviously that one tile is going to be huge, right? And if there's millions and millions and millions of tiles in this rectangle, then obviously they have to be very small to all be packed into the viewport. So, right now, we have some constraints that we're adding onto how these rectangles need to behave. For instance, if we make this rectangle smaller and smaller and smaller, eventually it gets to this like little 1x1 rectangle. And that is our furthest zoom, right? We're kind of constrained where we're not going to do any math and floating point. And so the smallest rectangle we can have is a 1x1 rectangle. That's an inclusive rectangle. So that means that all the points of the rectangle, all the bounds, are at the same exact location. They're concentric. Once we get this small, if we try to keep on zooming, we're going to flip the rectangle. The rectangle is going to invert on itself, and we want to prevent the rectangle from inverting on itself. So we need to add logic to stop the rectangle from inverting. So you can only zoom so deep, and then if you try to execute the zoom command, it needs to kind of ignore you, right? Now, for zooming out, we want to say that the camera can only get so large, right? Because we don't want the camera to be any larger than the world. So if the camera gets larger than the world, we got to shrink it down to a suitable size. And when we shrink it down, we need to make sure it's repositioned correctly as well. For example, if the camera is, say, in the corner of the level, and then we zoom out until the camera is its maximum size, the camera needs to be recentered, right? Because for the camera to be the maximum size, there is only one position that camera can exist in if one of the constraints is that the camera can only look over the level. And oh, I see that I'm not showing what I'm looking at. God damn it. I'll just explain this really quickly. We got a camera. If we pull in the border of the camera is looking at less stuff, therefore everything is bigger, right? If we have this camera rectangle and we make it bigger, then there's more stuff inside of it, so everything's smaller, right? And we're just making sure that we have some constraints on how that camera needs to operate, and that's what we're doing for the code. So I am sorry that I did not show that correctly. So let me just open up the little chat box here. Sorry that I suck at presentation. Yeah, so sorry. I'll get better. So anyways, this math here, we would just want to assert that the size corrections were correct. So it's the same if we have a width fix where we have a rectangle that was too large and we shrunk it. We need to say that, well, if it was a even rectangle, then we're expecting it to be exactly 512 in width, and if it was an odd rectangle, right, if the width was odd, then we're expecting to be exactly 511 in width, right? And that's because when we shrink and grow the rectangle, we do the same operation on each edge. So this +1 means that we're going to pull in this side by 1 pixel, and we're going to pull in this side by 1 pixel as well. So that means the delta for how much the sides of the rectangle can change when we're zooming in and out is always 2 pixels, because we have to account for both sides. And that's so that when we apply these operations, it doesn't change the centering of our camera, right? Our camera really has no... our camera has an implicit center point, but remember the camera is defined by the lower bound, the upper bound, and the lower bound and the upper bound on the X and Y, respectively. So now that this math looks like it's correct, the one thing we might want to do is for anywhere where we see, say, the width and the height, we might want to say, just color code that really quick and make sure that we haven't accidentally transposed the X and Y axes. And it looks like that looks about right to us. We see these are also X's, so we could make this, that's the wrong color, cyan, cyan, orange, orange. So everything looks like it's correct there. And that is a lot of code for just correcting stuff. So it's kind of like really bulky here, but we just gotta make sure that it's good, I guess. So this is really distracting, so let's get rid of that color coding here. So we see that right here we have a little commentary of like what's going on here. Did we wreck our rect? And the case here is too big. So we have these little commentaries for wrecking the rectangle. So this main, did we wreck our rect? And we have the case of inverting the rectangle right here. And then down here we have the case of making the rectangle too big, right? And then we have this main label here, so we can kind of identify these sections really quick, right? And see where these sections begin and end. And this section is way too large. We have too much error checking. It's not very efficient the way we did it, but we want the code to work first, right? First priority is get the code working. We can optimize it later. And also, this is just one camera object, so it's not like it's working on a batch of objects, and therefore we can have more branching and whatnot, and we don't really have to worry about the performance costs there. The first thing we do is we take the width and height, and then we decide, is that width odd or is it even, right? So the width odd will be flagged to 1 if the modulus with 2 ends up being 1, and if it ends up being 0, well then it's false, right? So is the width odd, right? And then width fix and height fix is just a flag to say, are we fixing the width or are we fixing the height? And so if the width is greater than 512, we'll flag width fix as true. Same thing with the height. We'll flag the height fix to true if the height is too large, right? And if one of those things are too large, we need to invert it. So we have some logic for how we're going to solve that, and we solved it algebraically. So the formula for solving that algebraically is we take the x and the y boundaries and we minus them and we add 1 to get 512. But we need some type of correction, right? So we have this u value. The u value is our unknown. So we're saying that when we pull in the rectangle, we want to pull in both sides by the same amount, right? Because that's just the way our rectangle works. To maintain the centering, we always have to pull or push the sides of the rectangle in by the same amounts. Because of that, right, we're going to take this upper bound that's too far to the right, and we're going to pull it back. And we're going to take this lower bound that's too far to the left, and we're going to push it forward, right? That's why I got this minus u and this plus u, right? And so the formula where we take these two bounds and we subtract them, and when we add 1, that's how we get the width. And there's a -1 here because if, say, the x and the y are both at 0, that's actually a thickness of 1. It's not a 0 minus 0, it's 0 minus 0 plus 1, because we have inclusive rectangles. So a single pixel, where the camera is on that single pixel, is a 1 by 1 viewport. So that's why we have this +1 here. Anyways, to solve this formula, the first part is we can just, add the 1 here and take the 511, make that a 512, right? Really simple, right? Now, to get rid of these parentheses around here, well, we don't really have to do anything to here. Well, we actually kind of have to do something to here. We have to take this implied +1 and distribute it and multiply it by both terms in here. And that's how we get the same thing, but we remove the braces. And then for here, to remove the braces around here, there's an implied -1 here that we have to distribute. So we say -1 times this, and then -1 times this. So it effectively kind of flips the signs in a way. But now we have this negative, and we have this negative here. I'm not really good at math, so I actually had to ask my girlfriend about how to get from this step to this step. I'm like, I know this is some type of distribution, but I don't know what the hell is going on, so can you help me, right? And so the next thing that we want to do is, right, we have these two u's. Now, to get rid of the u's, we just want to add a u and add a u to this side, right? So that's why we have the +u and the +u and got rid of the u's on this side. And then also we see that this 511, we subtracted it from here, and then we subtracted it from here, right? So we subtracted the 511 from both sides. Now, maybe we shouldn't have done 2 steps at once, because that can make it kind of hard to follow. But I think I covered enough of the math where it's easy enough when I'm explaining this. Really basic algebra right here, right? So we got u and u, so that can be u times 2. And then, now that we have this formula here, to isolate just one u, we just divide by 2, right? So now u equals this formula divided by 2. So this is the formula for how we are pulling that rectangle back into a suitable size, right? So now we look at our formulas, and when you're looking at, this formula right here, and you're wondering, well, what the hell is that? That's the formula that we solved. And we see this overgrow pole fix commentary right here. That corresponds to this little commentary here, right? So this is a big chunk of commentary. So this is already kind of like taking up too much space. So we just kind of exported this commentary into this like hashtag commentary section that's in the hashtag file. With that, after we pull it in, if sometimes we'll get a fractional value, right? So we want to make sure that the difference between the integer value and the fractional value is just 1. And to do that, when you cast a float to an integer, it immediately truncates it, right? And, hold on. Yeah, it immediately truncates it. That means these would be equal to each other. And I made a commentary that this is a delta 1. And if the floating point calculation and the floating point calculation is this one, and the integer calculation, if they're not equal to each other, then that means that the rectangle was an odd number of pixels wide or high, depending on if we're in the width or height section here. And if that's the case, we actually want to shrink the rectangle by just 1 more pixel. Or, hold on. That's actually going to make it... So we might be off by 1 here. We definitely want to shrink it by more when it needs to be shrunk. But that actually might not give us 511. That might actually give us, like, 509. Okay, we'll just run the code. Let's just run the code, kind of see what happens here. And also, today is my 1 cup of coffee per day. Or not per day. 1 cup of coffee per week. Okay, so we see that the index has failed. And I see that we have expected value of 511. But the actual value is 510. And, so let's think about that for a second. Expected value is 510. So, you know what? We might actually just not... Expected and actual. We're expecting 511, and we're getting 510. Okay, well, let's look at the code, because the code for our test might actually be wrong now. So, if we look at our test code, and that was, like, test case 3, we have this 9001 and... Oh no, test 3 here. So actually, the rectangle is... This is an even rectangle, so... you know, 100 to 200 and then plus 1. So if we open up a calculator here and just look at that, right? Lower bound, upper bound. So if we do something like, right, 200 minus 100 and then plus 1, right? Like, what is the width there? And this is why I need 101. So it's odd. So if this is an odd rectangle, then we're subtracting 1 here. So yeah, we are expecting to get something... We are expecting... Hold on. Yeah, I'm not sure... I gotta look at my diagram here. So that's a negative, so we're making it larger. It was already too large. And... if it's too large, yeah, I'm not sure what code is being executed here. And why do we have 99201? Let's just run this again and see what those outputs are. So this is the thing that sucks about, like, writing test code and then coming back to it another day. Because, like, you're not in the headspace for what all these calculations are anymore. And now you have to be like, okay, what are they? Because it is really simple stuff, but it's like I'm not in the headspace for it anymore. So we got, like, expected and actual values here. So what I'm really confused about is, oh, we're not even looking at the right test. We're looking at this one. And a rectangle that is all zeros, that would be a, that would be an odd rectangle, right? Because it's 1 by 1 pixel. And then if we do this minus an odd, then we have something that's even in the end. And if we minus, we're making it bigger, right? So it's a giant, big, even rectangle. Giant, big, even rectangle. And if that's the case, then we actually don't expect 510. We should be expecting, shouldn't we be expecting 512? Because we now have an even rectangle. Because we have this, oh, no, hold on. Because even though this is a odd number, remember, it doesn't matter. Because we always pull and push by, we take, if this were a 1, we would be pulling... we'd be pushing out each side by 1 pixel, so it'd still be an even amount, right? So if this is odd here, then the transformation we do it to here, we're still going to get an odd rectangle. And if we have an odd rectangle, then we'd still expect this though. So we're getting off by 1, where the expected value is 511, but we're getting 510 for some reason. And I don't know where that is, because our asserts are not failing us. And we got to think, well, where is that code for... well, let's put a breakpoint here. So this is for, like, if the rectangle is just too large, right? And if we look at our cases, shrink back to at least 512 by 512, translate back to the boundaries of the world space. So, so this is our first case here, is kind of fixing that problem. Greater than 512, and then we have all these asserts here. And you think that the assert would have caught this, so I'm not sure why we're getting like a 510 right now, because that's kind of telling me that this correction never caught it. If the width is greater than, and we have this... Did we possibly correct these values earlier? Did we correct these values, like, earlier up here? So we have... No, because this is making sure that if it's, inverted... And did we only solve for x here? Man, is this a disaster or what? Okay. Inverted. I see a whole bunch of X's, but I do not see any Y's. And that is concerning. That is concerning that I only have that. So, let's, yeah, we only have this case. So, did we organize things wrong? What did we do here? We were a little bit delirious when we wrote this code, weren't we? God damn it. Okay, so that's a problem. This looks like a serious problem. If the rectangle is inverted, if these sides are inverted, we want to fix those. I just didn't do the X code, it looks like. So, really quick, what we're going to do, like, we're going to take this. We're assuming that we cut and pasted everything. So, if we look for this, and we just replace the X's with the Y's, this is just a spot check to be like, do we have this code somewhere? And we just kind of didn't put it correctly? No. We just kind of screwed that up royally, didn't we? Okay, so what we're going to do is, we're going to take this formula where we solved for the inversion, and we're just going to put this somewhere. Invert, zoom, solve, or invert, zoom, I don't know. Invert, let's just do it invert zoom fix like this. Yeah, we'll just call it that, and then over here in our notes, we'll just take those formulas that we did, and we'll just kind of paste it in here, because we do not need to clutter this up already. I think the reason why we didn't know what we were doing, why we had this only for the X and not for the Y, is because we kind of, it's already so cluttered, we're just losing track of what's where, right? So, let's take this and just kind of paste it down here. And then anywhere where we see the X's, we're going to just replace those with Y's, right? So anywhere we see X's, we'll just replace with Y's. Really simple code, right? We're just going to change that, change that, change that. Okay, change that. Oop. And change that. Okay. So, you know, really trivial. The other thing is you want to remove these timestamps, because it's not true anymore. And I think what we really want to do is we might just want to say, we might just want to get rid of, like, all the commentary here. And just say, like, you know, at ditto y-axis, right? And what I'm saying when I say at ditto y-axis is I'm just saying it's the exact same math for the y-axis as it is the x-axis, so no need to add that extra commentary. Now, we have some clutter here that we gotta, like, clean up here. So we have this invert zoom fix. Let's kind of maintain these comments here. So, right, so for the zoom fix where we kind of, like, inverted everything, and the rectangle was inverted on itself, we want to, like, uninvert the rectangle, like, untangle the rectangle. So that's when we, like, pulled in the rectangle, right? We're zooming in, and we're zooming in, and the rectangle eventually is going to cross over itself, where the lower bound ends up being higher than the upper bound, and the upper bound ends up being lower than the lower bound, right? So everything's topsy-turvy world, and we gotta fix that, right? So we gotta pull that. So I did the math right here for that, and I just solved for the x-axis. So we might want to say, like, at vid integer ID, and take the time, the day, so 065, and the time is 1 hour, 8, or 1 hour, yeah, 1 hour, 8 minutes, and 55 seconds, right? So, and make a note here that if we zoom in too far, the rectangle inverts on itself, and the lower and upper bounds swap places. So, x0 lower ends up greater than x1. right? Just a little commentary about what we're doing here. And for ditto y-axis, all we want to do is say that we just want to say that this means if you see this, it means the math is exactly the same as the previous block, but the math is for the y-axis instead of the x-axis. When you see this comment, the y-axis block may be lacking commentary because that commentary only exists in the x block to avoid excess clutter. Now, I'm not sure if I like this kind of idea here, because I get that we're making the Y block less cluttered if we do something like this, but the other problem with that is now when we look at both of these blocks, one is much different visually than the other. So I'm not sure if I like that or not. I'm not sure if I want to stay with that kind of style, but it is nice to say, oh, the ditto y-axis, right? So when we look at this, we can just be like, this needs to be exactly the same kind of calculations as over here. And, you know, maybe this does offer some type of benefit where all these comments kind of are cluttering the flow. So if we want to understand the flow of the logic without being cluttered, we can just look at the Y logic and know that it should match the X logic. So I don't know if this is the best way to go, but that's the way we've kind of gone with this. And now that we have this zoom fix for if the lower bound is greater than the upper bound, so this is the lower bound and this is the upper bound. If these are flipped around, it means that we zoomed too far in and the camera inverted in on itself, right? So that's not going to fix our current problem, but it was obviously a missing piece of code. So we might as well just rerun, make sure everything runs, and look at our test case again and try to, like, figure out what the heck we're doing wrong here. And we've already decided that our test case is what... We've already decided that our test is correct, and it's the code that's wrong. So we have these expected, and this is index number 3 for our test, and we see the problem here is that this x1 and y1 value, we're expecting it to be 511, but we're getting 510, right? And I don't know why that is. I thought I had plenty of asserts to kind of figure that out, but I don't know. So if we look at our test, actually let's just, we got some breakpoints there, so let's look at the test code again. So this is index number 3, and we're expecting the 511s here, and we're getting 510 instead. And that's kind of confusing because, you know, we do this zoom here, and we're expecting to end up with a odd rectangle. And if we have an odd rectangle, we're expecting that when we pull it in, we're expecting to get something that's 511, right? So I don't know why the heck that is. So what we're going to do is add some more asserts, I guess. We're going to add more asserts because obviously I think we got too fancy with our asserts and then didn't catch something really obvious. So assert valid size correction right here. And we're like, oh yeah, if the width was odd, right? Or if the width was even, then it's going to be 512, and if the width was odd, then it's going to be 511. And that's all great, but at some point, it seems like we just screwed something up and we're getting this 510, right? And so that could just mean that the width fix and the height fix aren't being found, aren't actually being used. I don't know. So let's remove. Yeah. So this indentation kind of sucks because we're running out of column space. So I apologize. And I don't know, man. Let's just say, let's just kind of label this width fix like this. And we need some way to account for the indentation here, right? Because the indentation is crap right now, so we want to kind of augment it somehow with like some type of commentary that'll help us kind of see what kind of section of code we are in. And it's not the best, but let's just do this. So let's do like this, and then this was widfix, right? And what are we missing here? What's the difference between this style and that style? Because obviously we have some asymmetry here, but this is the same. Oh, are there two spaces here? Yeah, there's two spaces there. Okay, that's that. And then let's just take this, paste it down there. And this is height fix. Okay, so we got the height fix, we have the width fix, okay? And when we are in these sections, we're expecting to have one assert for an even rectangle, and then another assert for the odd rectangle, and if it's not either one of these, then we're saying, oh, that we did something wrong. But somehow we're getting a 510, so we want to just say, you know, that, you know, if the width is less than 512 minus 1, then we've made a mistake, right? Because we're getting that 510, right? So if it's less than 511, then it's a mistake. And we are thinking that maybe this assert will catch it, maybe it won't. And depending on if the assert catches this, it'll tell us something about where the code went wrong, right? So we'll just do error, shrink down, oh, I don't know, shrink over correction, I guess. How about too much shrink? I don't know. Too much shrink, and then, you know, x-axis, right? Okay, now that we have this, we're going to take this exact same case right here, right? A lot of redundancy, but I don't actually mind the redundancy, because it means that if we're checking the code for mistakes, we can actually check this block and just check this block and say, hey, is all the math exactly the same, except, you know, one is the x-axis and one is the y? So too much shrink y-axis and too much shrink for the x-axis, right? So let's see if that assert kind of gets tripped or if the mistake is somewhere else. Because I'm thinking the mistake is here, so I'm not sure why. Well, we'll see. I'm hoping the assert gets tripped because that'll be actually the easiest case. And unfortunately, the zoom test still failed. We're still getting that 511, 510, right? And so now the thing is, why is that happening? Is there any other place that we are changing these values? So we could just kind of go here, kind of highlight all the values that we're trying to look for changes. And we might want to say, well, enforce bounds has given us kind of problems in the past. What could be going wrong here? So when we are enforcing the bounds, I don't know here. It's less than 512 minus 1. I don't know. There's tons of places where this could be happening to us. And I don't know what kind of hackish things we want to do. We could get really hackish here, right? We could, let's get kind of hackish, I guess. Let's, yeah, let's, you know what? We're going to get kind of dirty here, but we're going to do it. We're going to do something really dirty, really ugly, but we need to figure out what's going on. So what I'm going to do is in tau type, I'm just going to say, like, I'm going to say that, you know, I'm going to make a private variable, AAC 2020, tau type, unit test, I don't know, unit test integer, I don't know, and, we'll just call this, unit test integer, and we'll say what test are we on, right? Hold on, let's just use our breakpoints here. This is in, rec zoom, So maybe we want to make sure that we can just see. We should maybe do this and say UTC rec zoom and then test index. And that's kind of like when we have a variable, we actually don't want any camel case. So this zoom actually needs to be lowercase. And this is, oh god, this is ugly as hell. But we're just gonna throw this in here, and we're just gonna say, you know, equals 0, or actually equals like a -1, right? Because it's not set yet. And then we'll do int32, and then over here we're gonna like define i32. Okay, and then over here we're gonna undef i32 like that. Okay, and we'll just say, you know, unit test debugging hacks, right? So these are hacks. We're just gonna throw this in here, and it's gonna get ugly because what we're gonna do is we're gonna look at those procedures, and if this index is greater than a negative, right? If it's 0 or greater, we're gonna like look at it and be like, is something going on here, right? Now, we might also want to say that, you know, define AAC 2020 tau type. Actually, no. AAC 2020 tau type. I don't know. Debug. I guess it's debugging the zoom, technically. Debug zoom, and then say that, you know, set that to 1. And let's just make a note of where we are, right? So, you know, at vid IID. And we'll say 0065 for the time, or the day. And it is 1 hour, 22 minutes, and 4 seconds, right? And throw in optional code, add code that is aware, make our functions aware that unit tests are running, and do extra checks dependent on what test index is currently active. So this is hackish as hell. This is very hackish. Very hackish, but whatever works, man. Right? We'll just roll with that. I mean, that's kind of crazy the way we're doing that, but let's just roll with that and hope that that kind of helps us out here. So now that we have this value here, this thing here, we don't have to worry about guarding it in the test. We just have to worry about guarding it in the main function to avoid kind of like using up extra kind of like processing power here. Now, yeah, so that just means that if we add special test code for this test here, then this test can't change at all, because we're going to like add these hard-coded asserts into the main logic. But let's take this, and in the test runner, right, this big loop here, we're just going to say that, you know, this is equal to ti, right, the test index. Bam! Yeah, this little test index. Nice. So now that we have this test index, we can kind of like try to figure out when things went wrong, right? Because we're getting that 510, right? And the most naive thing we can do for kind of like making use of this value is in here, we see this is our zoom pole, and this is where things are going wrong. We can say that, right down here, right down here, we can say that, you know, if we have this macro enabled right here, and should really cover that up so I don't get distracted, don't get demotivated. So if we have this, well, I guess feedback is good. So if we have this macro here, and it's greater than or equal to 1, then we're going to, like, do some extra checks. And if, right? So, unit test number aware debug checks. Unit tests, I don't know, unit test case aware tests, right? That's kind of what we mean here, okay. So I just want to make sure that when we're reading this and we're kind of grouping it, this is one concept, this is another concept. Because if we say unit test case, right, then that's going to be kind of like unit test case. That's kind of hard to understand, so we're going to put brackets around that. And if this test case is equal to 3, I believe. This is really large. Let's just say define test case or test index. And that's going to be too large, isn't it? It's going to like go. Can we just do TI for test index? Yeah, test index. And then right over here, we're going to do undef and TI test index, right? Okay, so this TI and if 3 equals TI, I believe, right? It's the third test index that's kind of giving us some trouble. So now we can like add some special code like right into the actual function, right? This is very tight coupling, and tight coupling isn't bad. Unintentional tight coupling is bad. So let's give this a run and kind of see like what happens here. And okay, so I just wanted to make sure that this test index is indeed 3. And the expected value is 511, and we're getting a 510 for the upper bound. So why would that be? Well, one thought is 0 to... everything is plus 1, so 0 to 510, is that actually even rectangle? Right? I think it is. So, or it's an odd rectangle? Hold on. So let's like, so, right, if we have 5, if, so we have 510 minus 0, but remember it's plus 1, so we're actually getting this, odd rectangle, right? And the odd rectangle is 511 in size. Ooh, okay, yeah, so 511 in size. Okay, I see. So now that I've kind of done that, and actually I think that my test case is actually wrong. So we have an odd rectangle, right? A 1 by 1, right? That's an odd rectangle. And if we have an odd rectangle, we would expect it instead of it being oh, got ya. So if we're gonna pull in more than it needs to be pulled in, then wouldn't that make it, if this is, so this is filling, this is making an even rectangle. This is an even rectangle, right? This is 0 to 511. This is the full bounds. This is, this right here is a rectangle as large as it can possibly be. If our boundary is, 0 to 511, right? That's a 512 by 512 rectangle. And that's an even rectangle, right? But we have an odd rectangle here, and when we modify it, we're always adding 2 to each axis, right? Because we're doing the push and pulls the same amount on each side. And so if this is odd, the transformation still makes it odd, and that means that in the end, we're expecting something that is, instead of 512, we're actually expecting something that is 511, right? And this is not 511, right? This is 0 to 511, but it's not 511 in size. This is 512 in size. So what we need to do is, if this is slightly shrunken a little bit more on the upper bound, then we need to slightly shrink this on the lower bound, right? This is 1 pixel pulled in on this. Actually, it's not 1 pixel pulled in at all, and this isn't 1 pixel pulled in at all. So remember that if it is odd, if the rectangle size is odd, we're pulling it in a little bit more than it needs to be pulled in. So this should actually be 510, 510, and this should actually be 1, right? So I think the math is still wrong because we're getting these expected 0 values or something. I don't know. But yeah, so we kind of screwed that up. So let's give that a run and see what we got. I think we're still going to fail on test case 3, but for different reasons. So let's give that a run and kind of see what happens here. Okay, so we have, yeah, for our expected x zeros, we have expected 1 and we have actual 0. So we're getting closer to where we got that 510, but it looks like the upper bound is not being treated properly. Or the lower bound is not being treated properly. And if we look at it, we have this u value, and the u value we're kind of like pulling in more, and that should be applied to both sides, but for whatever reason, it's not. I can think of some reasons why that might be, but we'll just say that, you know, if, since we have this hard-coded thing here, we can actually kind of check for what's going on here. So this is where we cast back to unsigned value. We can check the signed values, make sure that nothing wrong is with those, right? So we can just say that, you know, if x0, I32 not equal to 1, right, and we can get kind of verbose here. We can just say exactly what we expect. So we're kind of like rewriting this test case, but we're like hard-coding it in here, which is kind of ugly. But there's something, you know, wrong here that we need to address. So let's just throw this in here. And this should be 1, and this should be 510. And once again, 1 and 510. The other thing is that we're saying, before that even gets caught, we're expecting that 1 and 510 should give us something that's, or maybe that's not quite correct. 1 and 510 gives us... Aren't we back on an even-sized rectangle if we do that? So maybe that's why that's wrong. Maybe my math is still right. 510... yeah, maybe I'm just wrong there. It's on the corner. Yeah, because 510, upper bound -1 and then +1. That would give us a even rectangle, and we want 511. So, actually, this is incorrect, right? Never mind. So, let's just comment this out really quick in case we change our minds here. So, looks again like our test code is actually correct. And it's just a case of not having our head in the, we're not in the right headspace anymore. So if we look at 1 to 510, we're expecting a 511, 511 sized rectangle because it started out odd. And that would actually mean that we would be here. We would be here, yeah. Now that is kind of weird though, because, okay, so it's been pulled in, but why the asymmetry? We zoomed out. Well, that kind of makes sense. We zoomed out, and then we kind of pulled back in, and there's no way for that rectangle to be completely centered, because it's an odd shape, and that's why we have kind of this asymmetry here, where it's kind of like shifted. It's shifted over to the left a little bit and shifted up a little bit because it's an odd-sized rectangle. So by the nature, the virtue of being odd, it kind of has to be, doesn't it? Okay, so let's take that and kind of run with that and see. That should work, because we just we kept on thinking our test was failing, but it was the test code that was wrong. Now that we've kind of like wrapped our mind around that, right? Okay, so these were our basic tests right here, and then we want to look at if we're in the top left corner, top right corner, bottom left corner, bottom right corner, and we're growing too large. We want to test that we get values that are sensible. So how are we going to do this? Well, in the top left, that means everything is kind of like zeroed out. In overgrowing, we've already tested the case where everything is kind of 0. So we want to like test something kind of different, don't we? Well, I mean, if something overgrows... Oh, okay, it's not overgrowing the entire... It's not maxing out, it's just overgrowing over the bounds, and it needs to be readjusted. So, let's say we have a rectangle that is... so let's do X, Y, and then both at the same time or something. Okay, so on the... We'll just keep everything zeroed out here, and... Oh, well, the zoom pull is still kind of going to affect that, though, isn't it? By the nature of the way we did this and our constraint for everything being equal, yeah, by making sure the rectangle has to be square, there's some possible transposition errors we're not going to catch. Oh, well, I mean, this is the way we kind of hard-coded that, so for now, oh, well. So what we'll do is we'll say that if we have a rectangle that is 10 and 10 in size, and let's look at our diagram here. We want to make it a little bit bigger, right? We want to make it go overboard. So all these should be negatives here, right? Because we're going to overgrow. So all these things need to be negatives. Okay. And then we also need tests, inversion fix. Okay. And the inversion fix, those will be positives. So if the rectangle is in that upper top left corner, and we make it just one more pixel bigger, then what are we going to expect? We're going to expect it just to be shrinked back and to end up back the original size, right? Because we were already smushed right against the border. So we're expecting that if we kind of try to grow this rectangle, that it's just going to end up snapped back to its original size and in its original position is what we're also expecting, because it's already up against that boundary. So what we could do is we could just put a large value here. We could call it, 9090. How about 9090? Also over 9,000. And we're just going to expect the exact same values back, right? So let's give that a shot and kind of see if that does not crash, or if the code doesn't work, if our test case is making some type of bad assumption. I really don't know. So now, for some reason, we're expecting 9 and 5, 11 for test number 4. That doesn't make any sense. So let me look at the diagram here. So if we're going negative, we're going to make it larger. And... oh, hold on. As it gets larger, it's actually going to be allowed to translate, right? So as you kind of like grow that rectangle, it can translate to make sure that it's still inside the bounds of the world. So this is actually correct. And so we're just going to change it to, the expected values are going to be 0 and 511. That is actually correct. It's actually correct. But now we need to do something less extreme. So we're going to take these exact values, and we're going to do something less extreme that's not going to get that to happen. So we're going to expect that if we overgrow by 1 on each side, we're going to expect all this to... We're actually not going to expect the rectangle to shrink size. We're going to expect it to... We're going to expect that if there's enough room, that if we zoom in too much, if we get this rectangle a little bit bigger and it's up against those boundaries, it's going to translate over, but it's not actually going to shrink. So if we do this, we're going to add 1 to each side, and the rectangle is going to just shift over. So it's still going to be at this 0, 0 bound, but instead of being this being 9, we're going to add 2 to it, so 9, 10, 11. So now we should have 11 and 11, right? That is what we're expecting. We're expecting that the camera kind of repositions gracefully when we use our zoom and translation command. So now that we have that there, let's give that a shot and see if that is a sensible value, or if test case 5, if test case 5 fails, is it because our test is wrong, or is it because our code is wrong? So let's take a look at that. And test case does not fail, and that's what I was hoping for. Well, I mean, that's always what you're hoping for, right? Okay, so now that we have that, the next thing would be, what if we grow really large, but not like this much? Like, what if we do almost to the border, but not quite, to where we're like at, say 0 and 510, right? Or something like really close, right? Because we have this even rectangle, and this is thus an even rectangle as well. What if we just tried a really big number here, right? So we're going to still take these same inputs, and this is 10. So if we want to get to like 510, then we want to take like 500, divide it by 2, so 250. Right, so that's going to be 500. 500 plus the 10 we already have gives us 510, right? So it's almost kind of like getting to its maximum size, but not quite, right? And to get 510, that means that this is going to be 509, right? To get a 510 by 510. The idea is that we want to make sure that that overgrow algorithm is not being applied right now, because we're not actually overgrowing. We can still fix what's going on here by just translating the rectangle. We don't have to shrink the rectangle, right? Translation first is what needs to happen. So let's take a look at that and see if I got that math correct. I may have been off by 1. Let's just see what it says and then decide if our test is wrong or if the code is wrong or what the case is. So it looks like we got that calculation correct as well, so that's awesome. Now the next thing is, for the different quadrants here, we can actually take the exact same test cases and just kind of flip things around, right? So for the easiest thing, right, top left, the bottom right would be the easiest thing to do next, right? Because they're kitty corner from each other, right? And if they're kitty corner from each other, all we got to do is flip those x's and y's, correct? So let's take this bottom right here, right? Because this bottom right is going to be kitty corner from this. So we're going to take everything and we're just going to paste it kitty corner. So 0, 9 and 0, 9, it's going to be 9, 0 and 9, 0, right? So 9, 0 and 9, 0. Is that correct, or am I just making things up here? I don't think I'm flipping that correct, am I? This is the x. Okay, so it's not quite that it's not quite that simple, but if we do want to do the kitty corner version of this, it does make sense to be over here. So the upper bound, we're going to start glued to this corner, right? So 511 is the largest we can be on the X and the Y. And we want something that's 10 in size, right? So if we do 500 to 511, what do we got? We got 512, right? And we don't want 512. We don't want 511. Or, sorry, we don't want... This gives us 12 in terms of the width. We don't want 12. But we don't want 10. Sorry, actually, we don't want 11, but we want 10. So this should give us the 10, right? So, 11 minus 2 plus 1. So that gives us 9 plus 1, 10. Okay. So we'll do 502 and 502. So this is gluing us into that bottom right-hand corner. So it's the same thing as this, but instead of a 10 by 10 glued into that top left corner, we're gluing ourselves into the bottom right-hand corner. So these previous tests kind of had this origin of this rectangle kind of like glued up to the top left boundary of the world map data, and this test is going to look at, well, what happens if the rectangle is tangent to the bottom right-hand corner of our world map data. And how is that math going to work? Is it going to resize correctly, right? So when we zoom our rectangle in and out, we never want the rectangle to end up outside of the bounds of the world. We want it to gracefully adjust, so if somebody's just controlling the zoom or controlling the pan, we don't want just weird, erratic behavior in that camera. We want it to adjust gracefully. With these values, we need to also kind of do some type of extreme zoom first, right? We're going to try this one first. Right? We're going to try an analogous test. It's going to be, this test right here is going to be analogous to this test, but we want to just, it's analogous, so it needs to behave in a similar fashion, but similar fashion to how it behaves in this corner. It needs to behave in an analogous fashion in this bottom corner here, with how it behaves to correcting the overflow going over the bounds. So we know we need like a 10 by 10 rectangle, right? That it's still going to be a 10 by 10? No, it's not going to be a 10 by 10, right? We have this 511 by 511, right? Because we're just... Okay, yeah, so it should still be 511 by 511, because we're just zooming... we're zooming out so much that we're just filling the entire available space. So translation doesn't matter anymore, right? Because we're just filling all... Once we make the camera the maximum size, there's only one position it can actually be in. So let's give that a run and see what we can do there. See if that actually works. Okay. Okay, so that works. And now let's look at the next test here. We want to keep with this kind of analogy here, so let's just take all of this data here. Let's paste it down here to duplicate that test. And we notice that for this test right here, this is the test we want to reference. Instead of minusing this 990, we're going to minus 1 like this. And instead of getting a rectangle that is 10 wide, we're going to expect 12 wide, I believe. Yeah, 12 wide. Because we have this negative here, and if we look at the negatives are going to make it larger, so we're going to get 12 wide. And it's still going to be glued up to this edge here, right? So if it's still going to be glued up to this edge, the only way we're going to get 12 is if we make this a 500 and a 500, right? So if we take a look at that and run that, this test should also pass. And was that really the test we wanted to run? I think that's the test we wanted to run. Was that the analogous kind of thing? Yeah, that's analogous. Okay. Okay, so that still runs. So that's good. Okay, so now this last test. Let's look at the last kind of kitty corner test for that top left, and then try to make the analogous test for the bottom right. So now we're kind of minusing something kind of large. but making that viewport larger by 500 pixels, and then expecting that it's, you know, very close to being the maximum size, but not quite. So let's just take this 250 and paste this 250 down here. And then let's take these values right here. And it's still going to be sandwiched up against this this corner border here, this 511, 511. But we're expecting that these 500s are going to be really close to 0, right? We're expecting that we had a 10 by 10 rectangle over here. Well, hold on, no we don't. Okay, now we had a 10 by 10 rectangle. And we're going to make it larger by 500. So we're going to get something that's 510 by 510, right? And to get 510 by 510, well, let's just try 0 to 511 really quick. Is that 510 to 510? No, that's 512 by 512, correct? This is 511 by 511. And this is 510 by 510, right? So 511 minus 2, right, gives us 509. And then plus 1, 510. So we're expecting this test to also not fail on us. So let's take a look at that, see if that actually works. Okay, so if we give that a run, still works. Excellent. So the next case we need to look at is, we got these cases here. So let's look at the top right. So the top right is actually going to be a hybrid of the top. The top right is going to be a hybrid of the y's from one of these tests and the x's from the other test, right? So we can splice together certain aspects of both of these tests to get the top right test. So what's common here? Well, top is the common thing, so the top stuff, right? Well, what makes top? Well, top makes y stuff, right? So anything that is the y stuff, I guess because it's identical, we can't, so let's take this y stuff and paste it into this test here. So let's kind of like take this here, and we know that if we want to like integrate these tests to get those opposite corners, what we can do is we should just be able to say, here's the y stuff, which makes your top, and paste it up into here, right? Take that y stuff there. Now this stuff, we're just going to take it, and it's going to be identical. We're just going to take it and paste it down here. And then x and y stuff, so let's take this y stuff, paste it into here. And then right. So where's our right? So this bottom right. So right is determined by the x-axis. So we'll take the x-axis stuff right here, copy that over there. And then we will paste it into here, like maybe about like that. No, not quite right. Like that. Okay, so we're kind of off, but we were close. And then we also want to paste the x stuff from over here. It looks like we screwed up our formatting here. Let's fix that right now. So we have, this is aligned, this is not aligned. It needs to be aligned like that. Let's make sure that aligns, that aligns, that aligns. Okay, cool. So now we're going to take the x stuff from here. So this x stuff, we're going to copy that. And we're going to paste it right here. Okay, so now we've kind of spliced together those x's and y's. And if we've done that correctly, that'll just work. I think so. Unless I've done something completely stupid. Well, one thing that's not going to work is it's not a completely square rectangle, is it? Because of the way we kind of spliced that together. So we might want to turn off that assert somehow, right? We might want to say that, you know, if we're testing, we might want to, like, turn that assert off, right? I'm surprised that worked. Why does that work? That's surprising. Well, let's look at this. Why does that work? I did not expect that to work because we spliced everything together. Oh, yeah, because even though these aren't... because this is different and this is completely different, but this is still a 10 by 10. We still have a 10 by 10 rectangle. That's why that still works. Okay, cool. So, for the, for this test now, right, everything's kind of simple. We're just splicing together our tests, right, to make sure we don't have any weird transposition errors. Bottom left, right, so we need to take the bottom code for, bottom is determined by the y-axis, right, so we want to take this stuff here, the y stuff, and we want to paste it into here. So there's our bottom stuff for there. We want to take these exact values again. We want to paste them into here. And then bottom determined by the y, therefore xy. We want to take this y stuff. And we want to paste it into this test here like that. Okay, now for the x, it's bottom left. So it's not going to be this one, but it's going to be this one because this is our left calculations. We want to take the x's from the left calculations, right? So we take these x's, and we paste them into here. And then we want to take the x's from over, we want to paste the x's here. So remember, this is bottom left. So here's our left calculations, here's our x's. So let's take those x's and also paste them into here like that. And then we screwed up our formatting, so let's see where we went wrong. Looks like we went wrong here. And let's actually take a look at, these are the tests we want to check. But right for a second here, as we were cutting and pasting, it looks like somewhere we screwed up some alignment. And let's just do a quick sanity check and see, well, where did we screw up alignment? So alignment is correct here. Alignment looks good here. And then alignment here, the one outlier is this guy right here. We need to take that and move that in. Or not the insert button, the delete button. Hold on. So insert that. Okay, so now our alignment is still kind of off. Okay, so now we got all of our columns are correct. So let's give that a run and see if that works. And if that works, then I think that our test code for... No, we've done our zooming in and out code, but we still need to do the inversion tests. So, so inversion fixing, we got to say, well, what if we're... How do we fix a rectangle that's kind of been inverted? So the first task can be really easy. We can just say that, you know, everything's 1 pixel. And to invert, we got to pull it in, so we got to use a positive. So let's pull it in by 1 on each side. And we're going to expect that if we do that, we're just going to end up with the same thing because we can't invert, right? So we're going to just expect that everything is going to be in the same place, and that, you know, that's that test, really. It's that simple for that first inversion test of the rectangle. It's that simple. And if anyone wants to know, like, what the heck all these numbers mean, let me just go over that really quick because I see somebody kind of popped in here. So I'm going to show you what these numbers stand for. Let's look at our diagram. So we got this rectangle. And the rectangle needs to zoom in or out. So the rectangle starts this size, and to zoom in, we make the rectangle smaller, right? Because now it's looking at less stuff, but all the things that it's looking at now are bigger, right? So the extreme case would be if we zoomed into one single tile, then that one single tile covers the entire screen, so that one single tile is huge, right? So we've zoomed in. Now, if we zoom the rectangle to make it larger, then that rectangle covers a larger data set, it covers more tiles, and if there's more tiles seen inside of that camera rectangle, then they all need to be smaller, right? Because we have a whole bunch of stuff packed into here. So imagine that there's billions and billions of rectangles inside this square, then obviously they all need to be displayed very small if they're being mapped to the viewport, right? So these numbers here are test cases. So if we look up here, we can see this is test case number 1, test case number 2, test case number 3, or actually we're numbering them by index. So index 0, index 1, index 2, index 3, etc. They're all test cases that have been shoved into an array, and these are our inputs for the rectangle borders. We see x0, x1, y0, y1, and we can see x0, x1, y0, and y1 in our little diagram here. So these are the dimensions of the viewport rectangle, the zoom rectangle, and then we're either going to pull or push the sides of the rectangle, right? So if we do a zoom pull with a positive, that means we're going to pull in the sides of this rectangle, right? We're going to pull them in on each other, and that creates a zoom effect, right? Because the rectangle gets smaller. Now, the opposite of a pull would be a push, but to avoid having too many function names, I thought it would just be easier to just do the zoom pull with a negative number. And when we zoom pull with a negative number, it becomes a push, and we push the sides out, and we end up zooming out. So instead of having zoom push, I just say we just have zoom pull, just because I think it's easier. And then if we look for zoom push really quick, we just have this stub function. It says, do not use this, use zoom pull, right? So, you know, I want to make a note here that, you know, to push, use pull with a negative number, right? Make a little commentary right there, right? Since we've explained that. And right now, let's say the video integer ID in the bottom right-hand corner of the screen is 0065, and the time is 2 hours, 0 minutes, and 5 seconds. So if you ever see this commentary in the code and you want to know where we were explaining that, you can see it kind of right here, okay? And let's give that a little bit more padding. Okay, so let's go back to the test cases we were writing. And now we want to test another case where what happens when the camera gets too small. So you have this camera, right? And you're going to shrink it, right? To zoom in further. And then you want to shrink it even more. Zoom in further and further. And eventually it gets to its maximum zoom. And the maximum zoom is where the camera is 1 by 1 pixel, right? And if you go any further than that, the camera just flips on itself, right? If you take this lower bound and keep on moving it over here, eventually that lower bound is going to cross the upper bound, right? And this upper bound, if you keep on pulling it this way, eventually that upper bound is going to cross this lower bound, right? The rectangle is going to flip on itself. And when that happens, what will happen is the world, all the data you're rendering is actually going to get mirrored. And I don't really want to do any bizarro mirror world kind of stuff. I think that's just makes things kind of hard to comprehend. There's no need to do that. I think that's just kind of weird. And it's not going to be an odd behavior to say that when we zoom into the maximum zoom, the zoom command just stops working, right? It doesn't zoom anymore. That's not too weird of a behavior for a camera. I've used zoom controls in games before, and a lot of them have a maximum zoom, and it's not like, oh my god, the zoom's broken. You never think that. So this is a perfectly acceptable behavior to cap it once it reaches its max zoom. So let's think about, well, how are we going to reach that max zoom? So let's say that we have a rectangle that is, we already kind of are reaching that max zoom here, but we would like to do some type of calculation where we have the rectangle at a different corner. So right now this is in the top left corner, so why don't we do like top left, top right, right? So the top right corner is going to be moved over on the X. So let's take, this will be like, if we still want the like 1 by 1, right? Because we're trying to like test that pulling in, the maximum X value is going to be 511 and 511, right? 511 and 511, right? And now we are in the top, we're in the top right now, because we've shifted over the X coordinates, right? And we still have this is still a 1 by 1 viewport. And we're going to pull it in by 1 pixel. And we're going to expect it to be, we're going to expect that it's still going to be, this exact shape, right? Because this is as small as it can possibly be, so we're just expecting that nothing's affected, right? Okay. And we could do the same for kind of all these other quadrants, right? So let's give that a run, just make sure that that is a correct assumption, and then we'll do all the other corners, right? So the bottom left and the bottom right. Okay, so that looks like we got that correct. That passed. So let's keep on doing the same order. Top left, top right. So bottom left. How are we going to get to the bottom left? Well, the left is already here. We're already at the left. But to get to the bottom, we got to take these 511s and we got to paste them right down here, right? So that's how we're going to get the bottom left. Or hold on, that's the bottom right, isn't it? Hold on, I just don't know what I'm doing. Hold on. This is the left, this is the bottom. Okay, that's so bottom left, bottom left. Yeah, that's bottom left. And let's just zoom in with just the minimum amount of zoom to invert it in on itself. And then we're going to expect the same exact values, right? Because once we try to zoom in more than we can zoom, we expect that to be capped. Okay, let's give that a run, see if that works, and then we'll do the last kind of test here. And I see I have... I'm going to check my chats, because I see... Okay, yep, so that looks good. Let's do the last thing. So this bottom right. How are we getting to the bottom right? Well, we're going to do the maximums. So this will get us over to the right. And to get over to the bottom, we got to do this to get to the bottom. Okay, and if we do that, we're going to expect the exact same values. And we need to minus that. Okay, so that's good there. And somewhere we kind of screwed up our formatting here. Okay, there we go. So that works. And hold on. Let's see. One of these things is not like the other. Okay, there we go. So let's make sure that runs. And then we should try to make these values something besides 1. You know, some other type of ridiculous value, maybe. So let's say that, you know, this value is, I don't know, 999, or 9,990, or how about 9090? No, we already did 99990. Let's just do, like, 1, 2, 3, 4, right? Just make it a big number. And let's just make sure that that runs, right? Let's make sure that that very tiny zoom amount didn't have some type of special consideration. And this also, these numbers also exceed 512, and so that could trigger some type of case. So, okay, it still works. So the next thing we want to do is we want to add 4 more tests, because I think that, you know, as good as this is, it is up against those corners, and being up against those corners could kind of affect how these tests are working. So what we're going to do is we're going to take corners, and then we'll do, we'll make a note, top left, top right, bottom left, and bottom right. We'll make a note that what these tests are for. We're going to take these test cases, right? And to add more test cases, boom, we can just take that and paste it there. Isn't that nice? Like, that is what's nice about kind of making these little test tables, right? Like, our test cases are very dense, right? We can see, like, a lot of tests, like, in a very small amount of space. After duplicating these tests, we actually have to look at the macros that say how many tests we have, right? So if we look at our loop here, we can see that we have a number of test cases right here, and we've added 4 test cases, right? So we got to go over to this macro here. Instead of being 20, we're going to make that 24. We're going to run this because we just duplicated the test cases. So all those test cases we duplicated, they should still work. We shouldn't, and we also don't want to get any like seg faults or whatnot. So let's just make sure this works. And now that that works, let's just change this around here. So test case inversion fixes. So we actually still want to do these corners. It's just that we don't want it to be like smushed up against those corners, right? We want something where we want to like translate things diagonal, right? Let's translate things diagonal into towards the center of the canvas. When I say canvas, I basically mean the texture or the bitmap or the tile map, however you want to kind of interpret that. Let me check my messages here, because I think must not be the dude. Oh. That's fine. Okay, just checking my messages here, hold on. Okay, that's fine. Okay, so, these tests, we just want to translate, this is our top left. We want to go diagonally, right? So we want to go, we just want to get away from those edges. So we don't even have to think about going diagonal, we just have to think about getting out of that corner, right? So on the X, we just need to add. So let's try to do something kind of easy to comprehend here. So I think if we do tens would be easy, but now if we do tens, we're also... That also means that we are... Sure, whatever. Add 10. Just add 10. And... add 10. Just add 10 to everything. Okay. Yeah, just add 10 to everything. We'll still do the same kind of thing here. And... we're kind of just expecting it to be in the same place, aren't we? Yeah, I mean, we're not expecting anything kind of miraculous to happen here, are we? We're just expecting... Right, that's all we're expecting, right? And for this 511, we're in this other corner here, so anywhere we see the zeros, we can just kind of add tens, right? If we see it kind of... anywhere we see zeros, we can add tens. And then if 511... we gotta back off that 511, so we gotta subtract 10, right? So 511 becomes 501, right? 501 and 501 and 501 and 501. Oop, 501 and 501 and 501 and 501 and 501, right? And we can take all these values, and the idea is that after trying to shrink them, because they're already at maximum shrunkness, they're actually not going to change position or size at all. So let's take that and give that a run, and then also fix our formatting, because I see that we kind of screwed that up, right? So the formatting here is we want to respect the places, right? So this is the ones place, this is the tens place, and this is the 100s place. We want to respect that formatting. So we're going to have to fix this up a little bit. Okay, so that looks good. We'll double check it after we run this, right? So let's run this and see what kind of happens here. See if those tests pass. And if these tests pass, then we're actually done writing the tests for the rectangle logic, and we'll have to see where we go next. Okay, cool. So that's good. The rectangle tests are good. Now, the one thing we might want to do right before we exit is make sure we're not getting any false positives. So let's take this 501 and just be like 506, right? Make sure that crashes. Make sure that we don't have any tests that we... Right, this is in test-driven development, that's why you write the failing test first, so that you don't get any false positives. But we're not doing test-driven development, so we kind of have to be kind of hacky like that. So that is one good aspect of test-driven development, is that you can avoid those false positives, because you write the failing test first. Okay. Let's look at our agenda here, because I think we've hit like a little benchmark. Okay, we got those unit tests. That's what we were just doing, and it looks like we got to call tau sync. We got to call that once per frame. So let's edit this a little bit. So let's take this item here, and let's just cross that off. And it's no longer a doing, so we should also get rid of the doing here. Okay. So on 25, tau sync run. That's what we're doing. Let's go implement that. So it's not gonna have any like noticeable effect, but we can just make a note here. AAC 2020 tau sync run once per frame. Okay. So that's very intentional. And when we look at... If we look at our library chain, like how we're stringing together all of our libraries, you'll see that tau type is right here, but tau sync is here. And that's very intentional. The idea is we don't want the individual rectangles that exist on the texture memory to be able to sync themselves with the GPU, because that would be much too granular. It would if we put this after the sync, then it would allow us to resync the rectangles. It would allow us to resync the rectangles more than once per frame, and that would be kind of inefficient. Now that I think of it, though, how are we going to... If that's the case, that means that at this point, nothing is going to get to the GPU because tau sync doesn't exist yet. So we have like all the math for kind of manipulating this bitmap that needs to be synced with the GPU, but until we compile up to here, that does not actually happen. And that is kind of weird, but, you know, that's fine, right? Because the whole idea of this chain here is, right, is that we can compile any number of libraries and always get a working executable, right? Now, that doesn't mean that the working executable is necessarily going to be doing anything interesting, right? Because it's, you know, if we compile half the libraries, you have half of a project. You're going to be missing things, right? If you only compile this, you don't really have much. You just have this running executable that doesn't really do anything, right? The idea is that we just want to say that if we compile up to any level, the code will just, the code will still compile, and it won't do any erroneous operations. So let's glue that back together, and let's look at where we actually need to call tau sync. So let's look at our kind of bookmarks here for where we kind of were looking at things and be like, man, we wrote all this kind of test code, and then we never even used it, right? So we load it up. So you know what we should do? This is an interesting and hackish idea, but we never ended up needing it. We could remove, or we could keep it here for future reference to see one of our hackish solutions for when unit testing gets a bit difficult and we are okay, so I'm just gonna make a commentary here. Now that is kind of bulky. It's like maybe we shouldn't do that. Maybe we should just remove it. But I don't like to remove things right away. I like to... that is not correct. That is the time. The video ID is 0065. Oh, you can't even see this. Sorry. I'll fix that. So, in our code here, and I'll get better at this. I keep on screwing that up, though. In our code right here, we're not going to remove all this kind of cruft we added, right? It's guarded by a define anyways. We'll worry about cleaning up and optimizing things when we have an actual working product. No reason to kind of try to clean up this stuff when we don't even have a product, right? Like, why? Why would you do that? So, I think they call that calling the horse before the cart or something is the idiom for that. So let's throw that in there. We're not going to remove all of this define stuff because it is nice for reference. So let's open up our main file. So we have a main data file and a main function file that kind of glues together all these libraries and creates our main loop. And actually, no, let's not close that yet. So let's open up the main stuff and see, well, where does tau sync need to go? Do we need to make a macro wrapper for it? Like, what do we got to do to get it working? So in main, we have a main data file, a main function file. We'll keep the data on the left and the functions on the right. And is multi-threaded, blah, blah, blah. We don't need to look at the data. Okay. If we look at our functions, there's a lot going on here, but we basically need to find that, like, main loop, which is, you know, probably indicated by some type of while, right? And we got loop ticks. and handle input, game loop, etc. So I think what we can do is we can do the syncing. It could be a loop tick function, so we don't want to make our code too granular. And so we already have these categories of functions here, and we want to keep everything kind of as flat as possible. So if we think about it, the syncing function is really just a loop tick function, right? It's this function that we want to run once per frame, right? We want to run this once per frame, so it actually makes sense to make it a loop tick function. Now, technically, we don't... The loop tick function would just be a wrapper, but I think that to categorize it like that, to know kind of like what we're talking about, I think making it a wrapper function actually is helpful, right? So in our f macros, we're going to do f macros and tau sync, and we're going to do loop tick, right? And it's just a function that's supposed to be called in a loop, right? Now that we have this loop tick function, we have to actually create this macro, right? So this macro is just a wrapper for the AAC 2020 tau sync loop tick function, right? That's kind of how that works. If we look at tau type, we need to close that, right? Because we're not looking at tau type anymore. Let's just close all of... Oh, these are our notes. We can close this stuff. This is just a cut and paste thing. We can keep these notes here. Tau type. Close that. Let's open up the loop, the main tau sync. So we have tau sync functions here. And somewhere we don't have a loop tick function, right? And we gotta, like, make that. Now, the loop tick is going to call tau sync run. So when we find tau sync run, we know that that function, we're in our unit test, aren't we? That is, oh god, I should have went in the other direction. Okay, so tau sync run. We know that the loop tick function is going to need to call this. So, we need to go to the other side of this, right? We need to go... Oh, that's not too long of a function, is it? Why is it so kind of short here? And what is the section we're in? Init none. No, we're in GPU sync. And what is this guy? Is this like a... This is a helper. Oh god, like our helper function... Our querying function. Is this our querying function, or is this our... Oh, this is the private run function. Okay, I see what's going on here. And it's called GPU sync. Technically, this is not in the GPU sync section anymore. So let's put it over here. So let's just say loop tick. So this is a loop tick function, and I'll just put it in its own kind of section here. Yep. And also, I think, so let's say we do stuff for 16 hours. With that, if we do 10 push-ups every hour, then that would give us 160 push-ups. I think that would be kind of useful. I think I want to start getting more exercise because I'm getting chubby. So I'm going to do some push-ups after this. 20 push-ups. And we can increase the amount per hour later, but I think 10 per hour is easy to think about. Okay, so for this loop tick, it looks like it takes a U32, and it's a public function, loop tick, and it takes a U30, sorry, it returns a U32, it also takes a U32 called U32. And we don't really do anything with that U32, we would say, you know, if U32, and then reserved for future use. Yep. And down at the bottom of the function, we want to return just 0. We're not really actually doing anything with it. Okay, with this loop tick function, we want to do AAC 2020 tau sync, the public version, run, And we need to do a wet run. We have a wet and dry run. We need to know what those are, though. So if we look at the data for a TauSync, right? So we can look up TauSync and look at the data. And we can find out what we need to use. So we see we got this debug, we got a helper rectangle, and somewhere in here we have like the dry run and whatnot. And this might be kind of like in the wrong category. We kind of implemented this originally for unit tests. That's why we have the wet and dry run. But let's take that production macro and let's do define u32 and then define wet, and that's the wet run, right? And then over here we're going to undef u32 and undef wet, right? So that's for the wet run, right? So wet run and TauSync, right? So that's all we're doing per frame. And each frame of game, we want to resync any uniforms stored in texture with the GPU. And then we might want to make a note here that, you know, tau equals texture as uniform. Many times when I say tau, I am referring to the CPU, CPU pix, CPU side bitmap, or the GPU side texture, or either or, talking about them collectively. Okay. So make a note of what's going on there. It's not the best comment, but basically sometimes when I say tau, I just mean that 512 by 512 bitmap that is storing uniform values on the GPU. And we can make a note of when I kind of made this comment in case there's something extra that I have said verbally rather than in the commentary. So at vid IID, let me close my bash prompt here. So at vid IID 0065, and the time is, what is the time here? The time is 2 hours, 26 minutes, and 44 seconds. Okay. Yeah, so that looks good there. Now we actually have to make those F macros. So if we go and open up the F macros, we have a bottom and top file. So we'll go put the top file over on the left, because it's the top first and then the bottom. And what do we got here? So somewhere we have a loop tick function, correct? Yeah, we have these loop tick functions. And I really don't like the way I kind of like, kind of said it has to be this exact order. I don't think that was a good idea. I don't know if I'm getting any extra benefit out of this static assert. I get that I want to enforce some type of ordering constraint, and if I am doing it this way for everything else, it kind of makes sense to kind of just keep on keeping on like that. Now, tau depot loop tick. Are we actually doing tau depot loop tick? Let's look at the function file for a second. Tau depot loop tick. Yes, so we are doing a loop tick for tau depot. Now, what the hell are we doing in that? Like, why do we have a loop tick for tau depot? Hold on. I'm sure there's a reason, or maybe there's not, or maybe it's just like stubbed in. But is it doing anything useful, or is it just being stubbed in? So let's just look at for a loop tick. So loop tick in tau depot, and we have this loop tick and re-initting a init. So tau depot initted with set editor. Okay, so it needs to be re-initted, huh? Yeah, it has to be like rewired up. If the every time we switch editors to a new fragment shader, every time we switch editors, a new fragment shader is loaded, used as rendering code for Active Editor, and we need to rewire Tau Depot texture sampler, thus reinit. Okay, yeah, that makes sense. And we even have what date that was on and what video that was on. It was video number 41. We kind of don't have the same integer ID kind of commentary because this is an old comment, but that makes sense. So I just wanted to wonder. I was just wondering what that was, and that's sensible for what's going on there. And we won't try to fix that because it's actually correct. So Tau Depot loop tick, that's fine. Let's just take all this code right here, and let's just take and where it says Tau Depot, we're gonna just replace Tau Depot with Tau Sync right here. So anywhere it says Tau Depot is Tau Sync. And just get rid of all that orange in this section, right? So this is kind of tedious, but here we are doing some tedious things. Okay. This is no longer 22. If we look at our build file, or our main file, whatever you want to call it, we see that Tau Sync is 24. Yep. So currently it's 24. So in our top file, instead of looking for 22, we want to look for 24. And this is the kind of like error message. I don't think it needs to be in quotes, but that's what I did, so it's going to be that way. We need to undef this at the bottom. So in our fmacros bottom, we have loop tick functions, and it looks like not all of the loop tick functions are accounted for. So let's do a cs start here, cs start, for clipboard stack start, right? And let's go through kind of like all these loop tick functions and kind of rebuild that index of loop tick functions. So where is our actual... I'm a little bit confused here. Loop tick. It almost seems like there's no loop tick function up here. Why is there no loop tick function for this? So there's no loop tick function in here, and it kind of makes sense because keybox is not a thing that needs a loop tick function, but that's kind of really inconsistent here because everything else is loop tick. And even if it's like a do nothing function, I think that would be a valuable thing to do for consistency. So, right, because, yeah. Or would it be? I mean, maybe it's a bad idea. I don't know, but for whatever reason... Yeah, I don't know why I did this. I don't think this is a good idea. There's just nothing in here, right? And these are obvious. These are loop tick functions, right? We see these are kind of loop tick functions, so we're kind of like in the middle of multiple things right now, which we probably shouldn't be. Let's do no loop tick function for ikeybox. And I think we actually need to make sure that that is true. So if we look at the functions for ikeybox, it should just be like a data-only kind of thing. If we look at the functions for ikeybox, we see is clean, mark is dirty, right? We have these kind of utility functions, but there's no like loop function, right? Yeah. So let's take this, go TL CMD, convert it to lowercase, then to snake case, and then to uppercase. There we go. Let's paste this down here, right, just so these things match. I don't know how I feel about this, right? I think maybe we should remove this because there's no loop tick function. Let me think about it. Let me think about it. Let me think about it. Yeah, let's just remove this. Let's just remove this. And, because we know this section is basically loop tick functions, right? And, so let's just make this kind of a, I don't know how we're going to make it bolder than what is already there, so I guess we can kind of do this. Because we're out of indentation, it looks like. It looks like we're out of indentation. So we need to somehow make a section without adding any indentation, which kind of sucks, but I have these rules about how I want to not go over that border, so that's what we're going to do. We're just going to call it loop tick like this. And now if we kind of like take this and we kind of highlight this, does it get everything? Or no, it doesn't, does it? So let's just put an underscore like that, which kind of looks odd as hell, but yeah, sure. Let's just do that. That is kind of weird, but let's just go with that for a section. Okay. Okay, so now in TauSync, we have this TauSync loop tick and blah, blah, blah. I want to rebuild this index of functions here, right? Because I don't think all of those loop tick functions are accounted for. So we're going to do cs start, clipboard stack start, and we're going to start collecting everything that is in here. So we have these f macros loop tick, and we're just going to go control copy, control copy, control copy. Actually, that actually might be all of them, right? And control copy, yeah, because there's now going to only be 4, so if you do cs dump. But it was good to double check, so I'm not, like, mad about it, right? Yeah, so we actually had all these, and oh, hold on. Basунov loop tick. Oh, so Basунov does not actually exist anymore. 1, 2... Yeah, because that is now, like, CPU uniforms. That's what Basунov is, or maybe Basунov is now... Yeah, because this was basic uniforms, and now we have CPU uniforms. So this was, like, an old thing that does not exist anymore. So it was good that we kind of rebuilt that. So let's take that and just do undefs on these. And that looks good. We have some spacing problems. We have some inconsistency with our spacing. So let's kind of like clean up that spacing and make everything kind of a little bit more condensed, right? So we have that spacing. Okay, so our spacing is kind of uniform. That's good. Now, in our main function file, do we have that loop tick function? Yep, we do. And the loop tick function is going to call the wet sync. So if we look at loop tick, right, we do the actual live syncing function. Okay, so that's good there. Well, let's give that a run. See if everything looks good there. So I am kind of nervous because now this is like running every single frame, and it has like a little flag to know if it needs to be called or not. So let's just take that for a run and be like, oh boy, that ooh, okay. So something has gone wrong, and we know it's probably we know that it's probably like this run function, right? We know it's probably this, you know, syncing function. Oh, you know what? It's the, well, let's run this like that, right? We're gonna expect it not to crash. And then I remember we're not actually pushing up to the texture, right? We have to actually write that code. We never wrote that code, so we're going to have to write that code. And see, let's just see where that error is happening from. But I saw like, oh fuck, this code was never ran before. So that is probably what's going on. So let's take a look here and see what we got here. So no texture sampler paint 5D. I think this is fine. It's just this fatal error right here. I got this like whatever the hell this is, right? So what we're gonna do is we're gonna take this. And we're just gonna like find in files. And we're just gonna look for where that is. So find all. And you can see it's in one spot. And we have this texture push thing, and this is actually not done yet, right? It's like we have the correct size, and we actually have to push it, but something is wrong here, right? It's out of bounds. So if we look at the calculations here, we can see that we're checking like each one of these, if this, if that, if that, if that. And we have a lot of branching going on here. We could kind of reduce that because we really just care, are any one of these things out of bounds, right? So what we could do is we could still keep this here, right? And we could just do like if 0 and then or. And we can take all these calculations and just redo them one more time, right? And the purpose of this is we can, for the most common case, we're just going to reduce the amount of branching for the common case. Right? Because now, instead of having these 4 branches, most of the time, we're going to only have this 1 branch, right? 1 branch instead of all these branches for the most common case. And then, you know, if this ends up getting tripped, then we're already going to crash, so it doesn't matter if we have 4 branches, because we're in the middle of crashing, right? So the out-of-bounds x, and we can do like a OOB-x, or we could do pause x, right? And then we want pause x, we want pause y, and then we want the same things, but we want them for the negatives, right? So negative x and y. That's just the way we kind of ordered it, because these calculations are more similar. The lower bound calculations are more similar than the upper bound calculations here. And that's why I did x and y rather than the x's and then the y's. Because we usually do x's and then the y's, but in this case, because of the similarity of the formulas, we're going to do it this way. So let's take this, and we see that we kind of wrap these formulas. So we're going to take this stuff right here. We're going to paste that in there. Then we're going to take this next formula. We're also going to paste that in there, and we'll fix the formatting once we've kind of pasted everything into the place that it belongs. So, because we are kind of screwing things up kind of royally here. Okay, so if we look at that, we can kind of shift that around and say, okay, that looks good. So the upper bound minus the lower bound plus 1, upper bound minus lower bound plus 1, upper bound minus lower bound plus 1. It's less than 0. Oh, so this is just saying, you know, if we have... So can this actually go negative? Because PBR is like a pixel bounding rect, right? PBR, pixel bounding rect, and that's a rect type. And it's a tau sync rect, rectangle inclusive. And I don't know if that can actually go negative. So if we look at tau sync's data, let's just close this and close this. So if we look at tau sync's data, I don't think that type can go negative. So if we look at this, oh, so it's int 16, so yes, it can. Sure, I think that's a good calculation. Greater than or equal to 32. And let's just say, define, max width, 32. Max MS 32. Max side length. Technically, it's never going to change, so I don't know why we're doing this. Yeah, it's never really going to change, so we don't really need a macro for that. But it does kind of self-document that, so as long as we use a define, it's fine. But if you used a variable, then that would be a bad idea. So max side length, and less than or equal to 32, you know, ms, right? Sure, okay. And for these, what we're going to do is now we're going to log. Each one of these is going to turn into a log message so that we can see if we have multiple offenders. And then error, we can say that PBR pixel bounding rect invalid size, right? 2020. Okay. we have these log messages. Our log messages take a null pointer if it's not supplying any data. But we have enough room to where we could supply some data. So we could say, like, log out of bounds x, x1, and then we could actually put, like, what is that x1 value? So we could actually do %d \n, and then dereference PBR, and take that x1 value, right? And that's a little bit, and also that's not quite gonna work, is it? So this, let's just do OOB, right? Because now that we have this message here, we don't really need to know exactly, this doesn't have to be completely unique of a message anymore. And the reason why we want to write it like this is, I believe, for this to actually work, once we dereference it, we gotta, like, do some stupid casting magic, which is kind of annoying. I really don't want to do extra casting magic. So let's just do define LD and do AAC 2020. I know I didn't want too much, like, bloat in terms of these kind of, like, boilerplate functions, but it's really annoying me. So AAC 2020 tau sync, and then it's an info message, and it's decimal. So log decimal, basically. Undef LD. So log decimal. And when we log decimal, then we don't have to think about casting this, right? It's expecting that decimal value, and we don't even have to do the %d, do we? Well, to actually put it in a kind of a string like this, it kind of is helpful. So I don't know how we wrote our other log decimal functions, but we're going to keep it like this, right? And maybe that's not how we did it for the other things, but let's just do it for this. So we'll take this y1, right? And then we'll take this x1, and then we'll take the y1, right? So we got the y's, and we somehow screwed ourselves over here. We did not do this correctly, right? We can see that, you know, we can see that there's obviously a lack of, that the patterning is wrong here. We can see that we got these, so let's, actually, maybe we got that right. Let's see. So we have these x's. So if we subtract the boundaries, if it's greater than 32, we have a problem. If we subtract these boundaries, it's greater. Okay. Okay, actually, we did get that right. It's the uppers minus the lowers, right? So uppers minus the lowers, right? Uppers minus the lowers, and uppers minus the lowers. And if we look at x's and y's, x's, then y's, we can also see the same kind of striping pattern. Okay, so that is correct. So now let's actually create this info des function. So AAC 2020 tau sync info, and I think we have an info any function. So we're just going to kind of wrap this function. We're going to say, like, void, and we're going to take this function name and const char pointer strfmt, and void pointer dat des, and we don't need a wrapper for this because it's just going to apply the correct casts to call this. So we're just going to take this info any, and we're going to take the strfmt, and then we're going to say U64 would probably be the best for not mucking things up, and dat des, right? We're going to take that decimal thing that, well, it's already a void pointer, so that might still kind of work. Oh, no, because we're going to do this right here, is going to be a, we're just going to use int32. And that still gives us problems, doesn't it? That still gives us kind of problems, so let's just define int32 and define u64. Okay, so it's still going to give us some problems, but whatever. So undef i32 and undef u64. Okay. So i32 u64. Tau sync any, right? It's just a wrapper. If we got that right, it'll actually work, but I don't know if we got that wrapper right. We want to make a divider. Okay. So info decimal, and we're going to call it right here. LD, well, not call it here, but that's our wrapper. And then we're going to see, like, which things are out of bounds, right? And the out of bounds messages are wrong. So we got the x1, y1, and this should be, like, the x0, the x... Oh, hold on. So out of bounds... So OOB pause. It's OOB pause, right? And then there's x0 and x1, right? So out of bounds positive will print off both of those, right? So the x0 and the x1, right? And then for the out of bounds, for the negative, right? We're going to print off the same two things, but we're just going to make a note that this is out of bounds negative, right? And we'll just copy paste, right? So we'll copy paste this and change the x's to y's. Positive out of bounds. And then we'll take this and we'll paste it over here, and this is the negative out of bounds. Okay, so we got negative out of bounds, we got positive out of bounds. Okay, and we got x's and then y's, and then we have x's and then y's. Okay, so that looks correct, right? So just added some more kind of information to what's going on here. Let's just give that a shot and see if we kind of miraculously made all of our code correct. I don't think we did, but let's just see what happens. Makes a pointer from an integer without a cast. Okay, got ya. Okay, I see what's going on here. We were pretty close. We were pretty close to how we needed to do that, but not quite correct. So we have to expand the number of bits to be the size of a pointer. And then once you expand the number of bits to be a pointer, then we can cast it again. And we don't need to do this kind of extra scope here, or this extra parenthesis, but it'll make it easier to read for people who don't know the order of operations, or the order of precedence. So then we're going to take this and make this a void pointer, right? So it's because this right here takes a void pointer. So let's do that. And now... makes pointer from integer without a cast. So what are we doing here? Oh, so this is not supposed to be an i32 pointer. That's just supposed to be, you know, the decimal data. My bad. Okay, so now if we run this, I keep on making stupid mistakes. Okay, so it runs. Now we're going to get that error message again, hopefully. But now we're going to see, like, what is out of bounds. And now I'm seeing 0 to 31, 0 to 31. And that is correct, right? Out of bounds pause is, it says it's out of bounds positive, but that's just a 32 by 32 rectangle, and that should be fine, right? Now, it is kind of concerning that, well, I guess nothing's been synced, right? So the whole thing would actually be dirty. But that is a little bit disheartening or alarming that is kind of being pushed like that. So we might want to have some type of profiling where we can keep track of like a running average of what our average pushes to the GPU are. So now let's take a look at that, see why our calculations for the positive out of bounds are actually incorrect. So we take the x and we take the x's, we add 1, and then we have the maximum size is, you know, this 32. So actually, we need to be greater than that 32 to be out of bounds. Okay? And for this here, do we need to be less than 0? Oh no, actually we need to be, if we're pushing something that's 0, then that actually doesn't make any sense, right? Because now we're kind of pushing something that, if it's 0, we're not pushing any pixels, right? And that could be actually very error prone to do like a texture push with a rectangle that has 0 size. So it should actually be less than or equal to 0, right? If that's less than or equal to 0, we also have a problem. So let's take that and run with that and see if the code runs. And if the code runs, we actually want to make sure that we're not like that everything's working properly, like that we're not running these push commands like every single frame, right? Root of tree clean, skipping. So we kind of see these kind of skipping commands, right? So I'm gonna say that we're pretty good with that, where it is kind of, it knows. So we're gonna say that if we log this, we don't want to keep on logging this, right? So tau sync run. Yeah, so if nothing's changed, we just want to log this, but we don't want to log this all the time. So we'll just say that, you know, AAC 2020 tau sync clean messages ++ clean skip MSG. Okay. Less than 5, maybe. Then we'll do this little message here. And then, right here, if something was dirty, we'll reset this to 0, right? If something was dirty, we'll kind of reset that so that we can see it again. But if things are clean, we don't want to keep on spamming the console with this. So, you know, at vid iid 065, and the time is 2 hours, 56 minutes, and 56 seconds. Don't spam console with skip message. Okay, so that is what's going on here. It is the same kind of thing here and here, right? Right, it's the same commentary right here and here. Okay, we don't want to spam the console with that kind of skipping message. Okay, and we could make this like underscored like that. And that way we can kind of tell what that belongs to. And if we highlight this, now you can kind of see it in those places. And then we can make this a file scope variable in tau sync. So in tau sync data, you know, unit test, helper rectangle, we'll just make a misc kind of a thing. We have debug variables. You know, it's better just to make a misc section when we don't want to get too granular. So misc variables. Because at some point, we want to stop chopping things up and categorizing them. And we just want to be like, whatever, it's a thing, you know, whatever. I don't know what, but just, you know, it's a thing. Just throw it in there, you know? Okay, so misc variables and define i32 right here. and then undef I-32 right here. Okay. It's almost 3 hours, so I need to do 30 push-ups. So let's, I'm gonna do 30 push-ups after I get this running. So hold on. 30 push-ups. Okay, so now we got this thing to kind of help silence that message that's kind of in our logs. And let's just give that a shot and see what we got here, you know? Okay. Okay, so now that that's better. Or that's not really better, is it? It's, we're still getting... Oh, well, that's because, you know... we have to actually increment that value, don't we? I mean, you know, if we don't increment it, then, you know, how are we going to expect... If we don't actually increment it, it's never going to get silenced, you know, so that's just us being stupid. Okay, so now if we do this, we should see, like, that message pop up a few times, and then it's just going to go away, right? So if we look at it, somewhere we should see, like, a cluster of those messages. Yeah, so right here, it should be kind of, like, after a lot of those tests. Should kind of actually be after everything. Yeah, so tau sync, root of tree, clean, skipping, yeah, whatever. Okay. So I also see that it looks like we put a new line in that message, and it does not need a new line. So remove that new line. And then after this, once that looks kind of appropriate to us, we're going to do some push-ups. And we're just going to keep on going here. Okay, so that looks good. And when we look at the logs, right, this looks a lot better. Okay. Okay, so we got that, and tau sync is now in there. So if we look at our agenda screen, you can see tau sync run once per frame, and then we say we have this thing that says, you know, use W conversion from now on. So let's try to actually... I know this is kind of a random thing, but it's kind of a thing that if we add this in, it's going to help solve a lot of problems in our code. And it is kind of scary because we may have a lot of code that is doing this, but all of it is a problem if we're doing it. So let's go back to the bottom screen here for a second. And I need to do 30 push-ups really quick. So I'm going to get down on the ground, just do 30 push-ups. And let's make a little note here. I'm gonna make a little screen. I'm gonna make a new screen really quick, kind of black out and go silent for a little bit. So hold on. So okay, so we got some sound, and I'm just gonna make a text here. Okay, so let's put this right here. Let's also make sure we have the video ID. So, okay, so I'll be right back. I just gotta do 30 push-ups on the floor over here. Yeah. Hold on. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Okay. 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 So maybe I shouldn't, I should really, I should not, if I do have 10 push-ups on the hour, that'll actually be easy. Hold on, one more thing here. Let's make a note of how many I've done. Just Anonymous Pro, yeah. Today, total, today, 30. Okay, so let's just have that there for reference. And let's go kind of back here and think about what needs to be done next. And we kind of know. Okay. Whew. Okay, so we got those rectangle tests working, and let's check the agenda one more time. Okay, W conversion, we need to turn that on. But before we do that, we have something in kind of a stable state here, so we should probably kind of push that up. So git status, git add dot, git commit dash am, rectangle, zoom, zoom and translate tests done. Okay. So git status, git push GitHub master. And let me look over my test code really quick, make sure that that is correct. I believe it's correct, but if we look at our test code, we should have two big chunks of test code. So we have, yeah, we have a zoom, and then over here we should have another chunk. Yeah, so this is zoom, and this is the translate. So we have a section of zoom tests and a section of translate tests. And we see that we have 23 cases here. Do we have 23 for that macro? 24, yeah, because it's zero index, so that makes sense. Okay, so yeah, those tests are in fact finished. So what we can do now is we can push this up to git push kanji coder. Right? We'll push this up to the public because it's in a working state. Then we need to look at the if we're including the load PNG library right now in our kind of like our build script kind of thing. So I don't think it's in here. I think it's actually in the. Let's close this. We can close that as well. No, we don't want to save it. God damn it. So this should be in the, if we look at our library chain, libchan top, if we take that and we see our macro here, include load PNG. Right now it is 1, change that to 0. Give that a run, just make sure it still compiles, because now it's missing load PNG, and some of the things I wrote kind of depend on that. And I can see that implicit declaration of load PNG and code 32 file. So there's this thing right here, and we need to find, well, where are you being called? Because obviously you're being called somewhere. And where is that, right? And I know it's something that I probably depend on. So when we have something that we kind of depend on, we're going to have to like, we're going to have to wrap it, right? We're going to have to say like, save file, right? And in here, we're just going to wrap it, right? We're just going to say that we have this if-def for load PNG. It needs to be greater than or equal to 1 here. And we'll just do like, you know, if greater than or equal to 1, then we actually create this file. And if not, we need to like just log to the console what's going on here. So let's take this and do, you know, end if, and then take this exact thing right here and say that, you know, less than or equal to 0, and do an end if. And then let's just kind of like keep with this kind of like hashtaggy pattern, right? It's just like we want to make we want these if-defs to kind of like be glaring and shouting at us, kind of. Okay, so so we see test save file. I don't know how we're supposed to log this. So we're just gonna say, you know, printf PNG file is just a stub file. Printf, please include load PNG to fix. Printf by setting and let's just try to get everything kind of nicely aligned, even though it doesn't really matter, but, you know, this is the way I kind of write stuff. And then everything needs to be on a new line. Use up all our space here. Maybe we want to be really obnoxious and just be like printf, and then like do like stars and stuff. And then do some stars on the other side. And then maybe give it a little bit of padding, right? Just being kind of ridiculous, but printf. \n, give it some padding on each side so that it kind of stands out in the console a bit. Okay, so there are some other places where we have to look for this. So that's in load PNG, so that actually does not matter at all. So let's give that a run. And we're expecting that the code's still going to work, but that little test save file that we do in our code is not going to be, result is undeclared. Hold on, so what do we do here? Result. Okay, so int result is declared here, and I don't really like declaring something here and then, you know, doing it there. So load PNG result, what kind of value is it supposed to return? So if we look at load PNG on code 32 file, we gotta look at the documentation for that and just be like, well, what is it supposed to return if it's successful? And if we're just stubbing in the function, then we just want to be like, pretend it's successful, right? So if we look at load PNG and code file 32, actually we should just look at the, we should have just looked at our file, but since we're here, might as well, not here. Yeah, let's look at our code, right? Let's look at the actual source that we actually included rather than the, so load PNG and code file 32, no commentary here. So what about the same as load PNG and code file, but always encodes from 32-bit? Yeah, same as load PNG, but okay. Converts raw pixel data into PNG file on disk, same as the other encode functions, but instead takes a file name as output. Note this overwrites the existing file without warning. Okay, yeah. Now the problem is, So we got to look at the other encode functions, right? So we're saying that somewhere one of these encode functions should tell us like what it's returning and why it returns it. Okay, encode. Okay, so these are unsigned values. Okay, so we're gonna, so I think that it's actually returning a pointer? Unsigned, that's a really weird way to write it, or just write unsigned. So I think it means unsigned to a pointer. I don't know, int pointer? Shouldn't it be a byte pointer? I don't know. Return value. Load PNG error code 0 means no error. Okay, so that's what we're looking for. This is what we're looking for right here. 0 means no error. Okay, fine. So, we're going to take this result here. Unsigned int result. And it's actually a U32. So why don't we kind of do, you know, our U32 result equals 0x ff trap value. Okay. And the thing is, we're not really going to be able... Usually when we echo a result, we get a... we're usually looking at it in decimal, so we probably should not use a hex value. We should probably use, like, I don't know, 11223344. Something kind of, like, obvious. That's like, that's a very coincidental pattern. I think I probably did that, right? And we want to go up here and just say that U32, define... I can't type. Define U32. And then at the bottom of this section, we want to go, you know, undef U32. Okay. Oh, I kind of see that I'm doing it here, huh? So now that we've kind of added that U32 here, we're going to take this uint32 type. That's U32 here. We're going to remove that from here. We can keep the hex thing, sure, why not? But this define really belongs at this level of scope because it kind of applies to all these functions. And here we're just setting the result. And if we're in here, we're just going to say, we're just going to set it to 0. So result equals 0, right? And just say, you know, when load PNG is not included, we just want to pretend it returned success so that we do not crash the program. Okay, so that is what this is for right here. And we can also make a note of like, well, what time did we record this at? So at vid integer ID, and it is 3 hours, 17 minutes, and 18 seconds? 3 hours, 17 minutes, and 18 seconds. Okay. That. I'll just make a note of what we're referring to down here. Result equals 0. Okay. Now, let's give that a shot. Let's see if we've kind of stubbed everything incorrectly. And we're just expecting nothing to crash on us, right? We're like, oh, we didn't include the unused variable pixel height. And are we in test file, say, PNG 13? So I'm going to keep this up for reference. And test save file PNG. So we are here. And we can see that, you know, if we're actually kind of like, if we actually have the load PNG, we're using, you know, file PNG, and file PNG is just a define. So pixel array, pixel width, and pixel height, right? we're kind of using those. So we just have to kind of do a no-op on that, right? So if pix array and, you know, no-op, no. So make a note of, yeah, we have these no-ops, but why do we have these no-ops, right? So just a little commentary about why do we have these no-ops. So, so at vid IID, and the time is, what time is it? So the time is 3 hours, 19 minutes, and 29 seconds, and, what are we doing here? It's, the time, oh, wait, hold on. That is not correct. 0065. Silence the compiler. Right, that is what we're doing. Silence the compiler. So let's give that a shot. We might have to do... They might be pointers, and therefore we can't do address. Always evaluates to true. Okay, that always evaluates to true. So let's just do greater than 1 or something. I don't know. It doesn't matter, right? We just need some type of comparison. So just to make a note that, you know, why are we doing this no-op? It's because we have no load PNG, right? Okay, so let's just try that, and that might actually be a decent no-op operation here. The pixel array, error comparison between pointer and an integer, okay. So, so we just want to say, like, the address, or, you know what, we could just do pixel array, whatever, right? Just take something in there. And this pixel array, is that always going to be valid? Pixel array, unsigned char, pixel array. Ooh, we put that on the stack? Ooh, that might be a bad idea. Hold on. AAC 2020 to do man vital. A bit big for the stack. Right, that's a bit big for the stack. Should probably malloc that 512 by 512. We should probably malloc that. Let's just make a note of that. It's running, so but it could lead to some like mysterious crashes if we run out of stack space. So, yeah. So that's not a good idea. Okay, so now. Okay, so let's give that a run. So hopefully, eventually, we'll get this working. Okay, so things are working, it's running, yeah, and we can kind of see that somewhere in here. PNG file is just a stub file. Please include load PNG to fix set AAC 2020, include load PNG greater than or equal to 1. And then we could also include what file that's in. So it's in libchan.top right now. Now that may change, but we can do like a should be in libchan.top._. Right, and that may not be the case in the future, but that's where it should be. That may change, but, you know, things change, and that's okay. and it's better to have a whole bunch of, like, even if this changes, this is a better clue than just having nothing, right? And I get that eventually this may not be true, but, you know, the code isn't going to really change that much. The code isn't completely flexible and amorphous, so I'm okay with, like, hard coding little comments like that may change in the future, right? Because it kind of, like, helps us figure out where things should be. Okay, so now that it works, what we're going to do is we're going to go into our build script here. And actually, before we go into our build script, we need to get status. Git push GitHub and master. Oh, well, we have to git add dot git commit dash am about to add conversion error warnings. Okay, git push. Okay. Now, okay, so I see somebody just kind of showed up. So we're about to add some more compiler flags to find warnings, particularly the flag to check for implicit type conversions, because implicit type conversions have accounted for probably somewhere between 8 and 16 hours of complete headaches, because we made a stupid mistake. Our test code was doing weird things, and we just couldn't figure out where the problem was, because we had functions that took like 8-bit unsigned integers, and we're giving those functions signed 32-bit integers, and just weird things were happening, and we had no clue what was going on, and it was that. And that has happened to us multiple times. So we need to add that compiler flag to prevent that from happening in the future. So let's actually go into our build script here, and this sh file. So we should have an open with here. Open with, and open it with Notepad++. And we have like a lot of like compiler flags already. But the reason we weren't using the conversion error flag was because a lot of our code fails with that flag on. So we wanted to get our code to like a good stopping point, like a good stable point before we added this flag in, because we're going to have to fix some stuff, and this is going to be scary, because if we don't fix this stuff right, like we're going into these algorithms and we add some extra casting to prevent these warnings from showing up, we might make some mistakes, so we want to be very careful once we do this. But let's do, it should be like W error, so W errors. I don't think that's what I called it. No, because that's warnings are errors, and I don't even have a snippet for that. So I'm going to make a snippet here. So in my shortcuts here, I kind of like add like kind of snippets for like everything that I can't remember. So that actually is going to be this thing. So warnings are errors. Let's take this warnings are errors, and if I ever type W errors again, that's actually what I need. Now, in this file, we can see we got all these flags. We want something for like warnings for conversions. So W conversion, right? And oh yeah, W conversion, like that. So I already have it. So let me just mark this off here. Then I'm gonna put these back on my other monitor where I reference them, and we'll just kind of like put it in here. So W conversion, right? So this is gonna warn us about when we're doing really stupid stuff with mixing signed and unsigned types, because it's been hurting us pretty badly lately. So we want to kind of add that in, and we're gonna start to see some problems, because I did this earlier and I got a lot of problems. So let's take it and just give it a shot and see what we can see here. So this is kind of scary, because if we look at this, this is in, okay, it's not too bad. It's in JMIM string comparison, and it's actually, yeah, so it's not, it's in my my pebwalk file, that's what I am concerned, because that's the only file that has any assembly written in it, right? So there's like some scary stuff in there. If we look at our dependencies and we look at our peb thing, we can see that we have a target file, a target folder, and Windows 10 x64, right? So this is where we are kind of like targeting the current operating system of this number of bits. And we see this function, I see a function here, so I'm going to look at this function and find it and see like where we're making that mistake. And it is in the function declaration somewhere, so so somewhere in here. Oh boy, it's all over the place. Okay, we got a test it function, so it's good that we have a test for it. JMIM, whatever. Oh boy, this is a cluster of just horribleness. So we can see when we wrote all this, and we kind of sealed it off, because it's like, oh, we're never going to touch this, so just seal it off like this, and guess what? Now we're touching it. So right here is where we're having our problem. So we should probably take from here all the way down to here. And we need to, like, open this up, because we're about to, like, edit this. So let's just open this up and start kind of fixing this code. So this is going to get scary. We can see that it is on line 151. So let's look at line 151 here. 151. The character right here is a U, which probably means unsigned. Yeah, unsigned something or other. Unsigned short. And sub to get uppercase. Sub to get uppercase. Where are you declared? It also says it's also unsigned. So why is this a problem? Conversion to short unsigned int from int. So it looks like sub to get uppercase here. That looks correct to me. Right, because it's still a U-type. So I'm going to guess that, like, after we subtract these, that the result, for whatever reason, is an integer. And I guess I need to know my C a little bit better, don't I? Okay, so, because this is the limits of what this is are already kind of defined right here. So this is a wide string. So if we do this U-type here, unsigned short. Yeah, because wide strings are shorts. Okay, that's fine. So let's just do a cast here. So we're just going to cast. We're going to cast these calculations. Right? So we're going to take this calculation here, and we're just going to add this cast. And I'm kind of afraid that this is going to be like, this could take a lot of time. This could be like a lot of mistakes in a lot of places. So what we might want to do is if this ends up being a lot of things that need to be fixed in a lot of places, because we've never used this flag here. So this flag right here, wait, no, not here. So this flag here for warning us about implicit type conversions, we've been building this project for over a month, and we've never had this flag on. So we could have a lot of sites where we're screwing this up, and it could be a huge undertaking. But the thing is, this undertaking is not going to take a lot of mental power. It's going to be a whole bunch of very mundane stuff. And today is Monday, and Monday is the only day we drink coffee. So we really should not be doing any of this mundane, tedious stuff that just takes a long time but doesn't take much brain power. So, you know, we're going to fix this, and then we're going to turn that warning back off and just leave that on a to-do, because it's just going to get out of hand. It's probably going to spiral out of hand, and we just do not want to worry about it right now. So U undeclared. First U. Okay, so what did we do? So I guess right when we used this U here, we used it, and then we probably, like, defined it and undefined it right away. Yeah, so we see this define and undefined here. So what we're going to do is we're going to just change some of the formatting here. Oh, yes, caffeine, exactly. Yeah, you should, man. Or, I mean, I guess I'm making an assumption on your gender there. I don't know what you are. But yeah, totally, grab some. Okay, so, you know, since yeah, since, yeah, let's just kind of fix the formatting here. This is a very old formatting style. I know why we did it this way, but let's just, you know, kind of, like, change it around a little bit. So, oh boy, do we have something, like, way over there? Okay, so let's say that this is, wide string comparison, right? That's what this section is. This is a wide string comparison, and we can just kind of make a section here for wide string comparison. And some of this stuff is getting very ugly, right? Like, we kind of cut and pasted this, and the idea was we were going to cut and paste it, and we hoped that the code we were cutting and pasting was completely perfect, and we would never, ever have to touch it again. So we kind of sealed it off with this, like, commentary here, because it was like we were never going to touch this ever again, and then we're touching it again. So we can take this little commentary here, and we can also kind of cracked, open, sealed code. So we kind of cracked open this sealed code, right? So we can make a note that, you know, we've cracked open this sealed code here. And this is kind of like ugly. It's ugly as hell, but let's just roll with it and get it working. And I don't know if did I say Epilopig? I keep on pronouncing that wrong. El Papa Pig. To my in my defense, I am quite, dyslexic. So, yeah, you'll also kind of see me, sometimes I'll read numbers backwards. I'm not too dyslexic, but I do it. Now, I usually, like, if, I won't say that to an employer. I will not say, like, first of all, I don't want any special treatment for, you know, any type of oddities with my brain. Because, like, in high school, I did advanced classes and special ed at the same time. I did special ed reading classes, but then I did advanced math and advanced science classes. And so man, that shit sucked. It kind of sucked to be like, you get your A's in your science and math, and people would be like, oh, you just got the special version of the test, but you didn't. You actually, you know, because they think that you're in special ed, so you're taking, like, the stupid versions of everything, but you're not. But it gave me an interesting perspective, because I kind of learned that, you know, anytime you deviate from the norm, you kind of get... I'm not supposed to swear on this channel, I guess. Anytime you deviate from the norm, you kind of get screwed over. And it doesn't matter which side you deviate on. So if you're, like, really stupid, you're going to get hate. If you're really smart, you're going to get hate. And I think that, you know, you have to be aware of that, and also, you know, be more... whatever side, wherever you are, if you're a normal person, if you're a super smart person, if you're stupid, I think you need to kind of just, I don't know, not be a stuck-up asshole, right? I mean, not all jobs require a genius to do, and being smart does not determine if you are a good person or not. So, like, we like dogs and cats, but I'm sure they're, you know, they're not as smart as us, right? But it's not like we're like, oh man, we hate you, right? So, I mean, same thing with somebody who's less intelligent than you. Like, somebody who's less intelligent than you can be, like, an awesome person, right? And somebody who's super smart could be, like, basically, like, a crazy, evil supervillain, right? So it's like, I don't think that intelligence should be used to, like... Intelligence shouldn't be this, like, one metric we use to evaluate the worth of human beings. Anyways, I shouldn't say that too much, because that is kind of slightly political, and I don't want to get political. But I don't think that's a controversial thing to say, so I'll just say it, right? Okay, so anyways, so here we're kind of, like, opening up this section, and we have this kind of U here, and this U is unsigned short, and now unsigned short should just be 2 bytes, right? And let's just check that really quick. Unsigned short should be 2 bytes because it's like wide ASCII. Size of unsigned. You know what? Screw that. You know what? We're not even going to do that. You know what we're going to do? We're just going to, like, right here, we're just going to say, in our unsigned thing that we're kind of doing here, we got these defines here. We're just going to be like this. You know, screw that. We're just going to be like right here. We're just going to be like assert, and then size of u equals 1, right? Or 1 equals size of u. Might be. Okay. That is our assumption, right? And if that fails, then we have some problems. And then over here, we're going to just do define u16. I don't even think we have a define for u16 because it's not something we use. So let's just say define u16, and we'll say that for now, since I don't use this much, I just see unsigned short here. I'm just going to throw it in as unsigned short. And, I mean, this is for a 64-bit operating system, so it's not like we need to worry too much about a type def for this to get the proper bit widths. Like, if it's proper here, it's always going to be proper because we're targeting a very specific operating system. And then undef u16 here, right? So we got unsigned 16. This is a wide ASCII. So we can make a note here that u16 equals wide ASCII. Okay. So with this u16 wide ASCII, where are we using this? We're using it right here. This define doesn't exist up here, so we're going to do u16 right here, and then u16 right here. And this formatting is ugly, right? Because we kind of like are breaking into some really old code, and we had slightly different formatting when we wrote this. So let's just give that a shot, and what we're hoping for is to make sure that the compiler isn't complaining in this section of code. And oh boy, we just mistakes all over the place. Yeah, so this is really going to cascade all over the place, and I really don't want to deal with this because this is our 1 caffeine day. So we kind of see, okay, this character minus that character. It's, I guess the result of this is an integer, and then we have to cast it back to. I did not know that that's how, okay, so now I kind of see why C does not have sane implicit type conversion rules, because I heard about that. I'm like, what, really? And now that I have this warning on, I'm like, oh god, it doesn't. So let's try to just get this function to stop failing, and then this is going to just be a thing that we're going to have to, like, do all the time. This sucks. Conversion to int from size t. Oh, just screw this. Okay, so this is going to just be a thing that is going to plague us for the rest of our life. Okay, yeah, that sucks. So we're just gonna have to hack away at that every once in a while and just hope that we can kind of get that working eventually. So let's go into our build script here. And just be like, man, this sucks. How are we going to... yeah, we have to just kind of... I think if we... Well, line continuation... Yeah, so we have to just take this and... I'll just paste this here and make a note of this. So we'll just say, if you are tired... Here is some busy work. Turn on. And start fixing where things break. So yeah, so this is just some busy work here. Because yeah, this is gonna plague us for a very long time. That really sucks. That really sucks that it's gonna like plague us for a very long time. So our assertion kind of failed here. So, line 136. So that's a good thing that we made that assertion. And also I know why the assertion failed, because we did the assertion and then we put 1 when we were supposed to put 2. Alright, because the idea was that this is a wide, right? So we're saying that, oh, this is a wide ASCII, right? So wide ASCII is not 1 byte. It's 2 bytes. Okay, so give that a run. And now that should work, right? And then we just want to make sure that the project actually just, compiles and whatever. And then we're going to put load PNG back in, right? We're going to put load PNG back in because we don't want to keep certain things just commented out, right? So we're going to go back to our load PNG that we kind of commented out here. We're just going to put that back in, because we're not trying to fix the conversion errors anymore, because it's just going to take us a long time, and now we just got to be careful. Now, unfortunately, we just got to be careful. We're going to just kind of like, we're probably just going to get screwed over, honestly. We're going to get screwed over more times because the compiler is not going to catch these mistakes, and it's going to be up to us to write good tests, and tests that can kind of catch when we're kind of doing, when we have problems with implicit type conversions. We're just going to have tests. We're going to need testing code that's going to be able to catch that. And so it sucks that we're not going to be able to use that compiler setting, because we've kind of dug ourselves into too deep of a hole for now. And we may never get ourselves out of it, because we're going to keep on writing code with those mistakes, I'm sure of it. Because I don't have enough experience to know exactly how strict I have to be with the casting to get that to work. So that sucks, but whatever. So let's just do git bash here. Let's commit that. And git status, git add dot, git commit dash am, and just say can't use w conversion with compile. So we just can't use it, unfortunately. It's just too much of an overhaul. Git push. It's too much of an overhaul, and it's busy work. It's busy work that we should not be doing today. So git status. Let's do a git push to kanji coder. All right, so this is the public place. So if you want to know where I'm like pushing this up, like if you have Windows 10 64-bit, you can go to tinyurl.com/git-aac. It's displayed in the bottom right-hand corner of the stream, and I'll just put it right here, www.tinyurl.com/git-aac. Like, if you want to take a look at that, I have kind of put it out there for people to take a look at, because I figure the most important thing is not really, for this kind of project, is actually not having a patent on it, but rather just being the first person to do it, right? So, let me check my messages here. I'm messaging someone on Twitch right now. Cool deal. Okay, so let's see where we are here on our agenda. I like how I got this little horse kind of over here. I thought my background was supposed to be changing. Has it been changing? I just haven't been paying attention, probably. The agenda now. Agenda screen. So this W conversion thing is, we're just kind of screwed with that. That'll just be a to-do that we have to eventually fix. And we can see that, oh, camera, Paint 5D, tile camera, keyboard inputs. Cool! So we're actually on the next sprint. So that's pretty cool. We're on the next sprint. And since we are on the next sprint, we should probably stop the stream and restart it, because it's kind of like a new section, right? We're in a new section here. So let's, first of all, let's take this and this list here and kind of clean it up. Like, we have all this stuff. Let's just, we're kind of done with this sprint. And this is just a to-do forever, right? A forever to-do. Alright, this is a forever to-do. We'll put this down here. And then, let me just cut this out for a second and edit it in a proper text editor. So sprint number 5 is what we're on. Paint 5D camera. Okay. So let's take, so this is the next thing we're doing. I don't know if yeah, so this is what we're on now. This is the agenda. And we are done with this recording. I just have to change some things around. So let's do yeah, so let's do the next time. I have like an agenda next time. So we're gonna be right back. And this is not the next time. So let's look at our agenda screen again. So this thing needs to be changed. So this is now sprint number 5, and what is it called? Paint 5D camera. So we're gonna change this to sprint number 5, and it's Paint 5D camera. Okay. And then if we look at our agenda next time, sprint 5, Paint 5D camera. Okay. So we're ready to... Actually, let's kind of move this around. I think that's kind of... We should kind of like... kind of move this kind of like over here, right, in the corner. It's been in the corner, right, where you can kind of see where it is. So let's kind of like just move that kind of over there. Okay. So the next sprint is Paint 5D camera. So we're going to shut down this stream. We're going to increment the number, right? We're going to be like at 66. Be right back. Restarting stream since we are on a new section. Okay. So let's do that right now. Okay, I think I'm ready. Okay, I'm ready. I'll be right back. This will be like probably take at most 5 minutes, maybe a few seconds, anywhere between a few seconds and 5 minutes. So I'll be back. I hope to see you, El Papa Pig. Okay, so I'll be back.